Hi everyone and welcome back to PrepFusion. So today we'll start a new topic from COA and also it is common to digital electronics, that is IEEE floating point representation. Okay, so this video will completely cover that, but before starting that floating point representation, I will start with the basics of number representation. Okay, that already has been covered in your digital course. If you want to cover it comprehensively, number systems, you can check out our digital course, but this I will cover the basic overview of number representation, signed number representation, and then I will go to our main topic, that is floating point representation. This will be the lecture 1 where I will go with the overview of the number systems, okay, number representation, and in the next lecture we'll start with floating point representations. So in our EC syllabus, for number representation, right, we have binary, integer, floating point numbers as explained, and like all these have been covered comprehensively in our full course. I will just go in the overview of this for you to get to that level so that you can understand the floating point representation. Okay, because few COA students also will be studying, so I had to cover this lecture 1 basics for those students who haven't studied number systems from our course yet. Okay, if you haven't studied, you can go and study that. Okay, and for if you are only preparing COA, you can just watch this lecture and that's it. If you are preparing digital electronics and COA both, you should study the number systems and then you can go through this lecture 1. Now lecture 1 will be just overview, basic things that already has been covered in number system. I will go in the overview, so you can watch this first lecture in 2x or just watch the notes, okay, so that you just get an idea like what I have covered, and it's like that you haven't missed anything. Okay, that is the most important part. From lecture 2, new content will be coming. Okay, this is just a summary and overview of number systems that already has been covered in digital electronics. So I will quickly go over everything, okay, that you already know. So first is why do we need number system? Like, number system is a mathematical way to represent numbers using specific symbols and rules. We have to obviously specify like quantitatively what exactly this is. This is a single mobile phone, so we have to quantitatively say a few things. That's why number system was required. And in digital systems, it is also very important how we represent the number system, right? That's why representation is also very important, because our digital systems and our computers, it can only understand ones and zeros. So you have to be more technical now. What does ones and zero means? It means binary. So our digital systems can only understand binary. So how do we represent numbers? Like, what kind of numbers? We have negative numbers, we have positive numbers, we have fractions. Okay, we have irrational numbers. So all these rational numbers, all those things are there. How do I represent in computer systems and digital systems? That we learn in this whole lecture series. Okay, so there are mainly 4 types of number system that we already know. First is binary, that is used in the computers. That's why it is very, very important. And octal, decimal, hexadecimal. Okay, so in binary we have 2 digits. We have only 2 digits. What are those 2 digits? 0 to 1. In octal we have 8 digits. What are those? Those start from 0 to 7. In decimal, this is the number system that humans use. Computers use binary, right? So humans use decimal, so it has 10 digits. That's why deci. Zero to 9. And hexadecimal has 16 digits. Okay, now how do I represent 16 digits, right? So first I go from 0 to 9, then what are the remaining digits? 6 digit 6 digit is left, right? So how do I represent 6 digit? I start from A, B, C, D, E, F. Sorry, not 6, sorry, 5 digit, right? Because 0 is also here, right? 0 is also here. So A, B, C, D, E, F is left. That's how we represent the other. So what is this? A is this basically 10, right? And F is 15. Okay, in decimal. So that's how I represent hexadecimal. It has 16 digits. Okay, this you already know, so I will just blaze through these things, definitions and all those things. So first is binary system. In binary system we use base 2. What is base and all those things, that has been explained in our comprehensive number system lectures. Okay, I will not go through that because I want to quickly go through this lecture, right? Because this is just the basics portion. So just think this, just the main thing is it is base 2. Base 2 meaning I have only 2 digits. Okay, one is 0 and 1. So how can I represent the numbers? So I can start with 0, 1. Then how can I increment? So I will add a 0 over here, and that okay, then I can do 1 0, right? then 1 1, then 1 0 0, then 1 0 1. So like this I can go on. Okay, so this is how the numbers are represented in binary number system. Okay, we add 1 and zeros, that's it. Then we have like octal number system. Okay, I will tell you how to convert from binary to decimal. I will go over that quickly. Okay, so octal number systems, I told you, right, it has 8 numbers from 0 to 7, and it is like, how do I represent the number here? From 0 to 7, it is, this sequence is correct, right? Then after 7, what will come? After 7, 1 0 will come. Okay, I increment the next bit, right? The next bit, I add an extra bit to increment. Then again, I will go with the same flow: 11, 12, 13, 14, 15, 16, 17. Now I will stop here 17, right? I cannot write 18 because 18, writing 8 is not allowed in octal number system. So what I will do is I will increment my MSB, right? So this will be incremented. So this will be 21, 20 now. This will become 20, 20. And then again it will go on 21 to 27. Then again it will become 30. Okay. So I cannot represent 8 in this octal number system. Binary, you already know. Binary is self-explanatory. I don't have to explain this. Okay. So hexadecimal. How do I represent hexadecimal? So from 0 to 16, this is 16 numbers, right? From, sorry, not 16, 0 to 15, it is represented. Then after 15, how will I say? Again, I will add a MSB. So it will be 1. MSB will be 1. And the last digit will be 0. So after F, right, 1 0 comes. Here after 7, 1 0 comes. Okay. And here after 1, 1 0 comes. Okay. So you have to be very, very careful about these things. So F, then it is 11, 12, and it will go on till what? Like some point will come, right? 1 9. After 19, what will I write? So actually in decimal, I should have written 20, right? Decimal 20. But we are in hexadecimal. So it will actually become 1 1 0. This 1 0 is represented as A. Okay, this 1 0 is represented as A. After 9, A comes, right? So that's why I will write here A. After 9, A comes. So I will write here A. So then this will be 1B, 1C, 1D, and 1E, and 1F. Okay. So yeah, that is the case over here. So we have got our 5 digits. So next, next what will happen? Next again, this will increment. This will increment. So this will increment to 2 0. This will increment to 2 and 0. Okay. After 1F, this will increment to 2 and 0 because the MSB I will increment. So this will increment to 2 and 0. Then it will become 21, 22, and so on. Okay, I hope you understand the digits, and now I will tell you how you can do the conversions. Okay, so if it feels like I'm going fast, because I'm going fast, okay, because these are basic things, I don't want to waste too much time here. I expect that you already know all this. Okay, so here I want to do conversions. Okay, conversion to decimal number system from any random number system. I just need to know the base. That's it. I just need to know the base. So what we do, we multiply each digit by b raised to power n. What is b? B is the base of the number system, and n is the position of the digit starting from 0. So if I have a number like this, right, 1010, how do I convert it into decimal number system? I simply do this thing, right? I simply write the positions. This is 0 bit, this is first bit, second bit, third bit. Okay, and then what is the base? Base is written here, right? Base is 2. What does base means? How many digits are there in this number system? 2. Okay, so then what I will do, I will just multiply this 0 with the base raised to power n. N is the position of that particular bit, that is 0th position, right? Then again plus, I will add each up. Then I will multiply 1. 1 is here, and what is the position of this bit? Like this is the bit. Okay, I will place this bit here, and then I will multiply by the base raised to power the position of the bit. Position of the bit is 1, so it will be 1. Then plus 0 again into 2 raised to power 2 plus 1 again into 2 raised to power 3. Okay, so it comes out to be 8 plus 2, simply 10. Like that is what is written in the example. So I don't want to elaborate too much. So here also we are doing the same. So converting anything to decimal is very, very easy for me. What I do, I just find out the bit position. This is 0th bit position, 0, 1 and 2. and then I find out the base. So base will be always here, okay, base will be always here, and then what I do, I raise the base power to the bit position. So in the 0th bit position, the value of the bit is 7 multiplied by the base raised to power the bit position, that is 0. It is 0th bit, right? Plus this first bit position is 2, so we write 2 here, and then I will multiply 8 raised to power bit position, that is 1. Okay, so that's how we convert from any number system to decimal. Converting anything to decimal is very easy. But what about other conversions? If I want to convert between octal to binary or binary to octal, how do I convert it? Sorry. So for converting from octal digit to binary, what we write is, we write the 3-digit equivalent of binary. What do I mean by this? So what is 0? 3-bit representation binary equivalent of 0? It is 0 0 0. What is 3-bit representation of 1? It is 0 0 1. And 2 it is 0 1 0. 3 it is 0 1 1. 4 it is 1 0 0. 5 it is 1 0 1. 6 it is 1 1 0, and 7 it is 1 1 1. So I am using all the 3 bits every time, right? So that's why what we do for converting from octal to binary, what we do, we just simply write the 2 as a 3-digit equivalent format. So what is the equivalent 3-digit binary format of 2? It is 0 1 0. So I replaced here 0 1 0. And what is the equivalent format of 5? It is 1 0 1. So I replaced with 1 0 1. Then what we do is, one thing you know, right? If I am writing here 10 or 0 1 10 in decimal, right? This is in decimal, okay, don't get confused, this is in decimal. And 0 0 1 0 in decimal, does it make any difference? So if I am writing 9 and 0 9 and 0 0 0 9 and 0 0 0 0 0 9, does it make any difference? No, right? It doesn't. It's still a 9, right? So what we do is, we neglect the left hand zeros. We neglect those, okay? We just neglect and then write the final format. And if you just want to convert it back, how do we convert it back? What we do is, we group the binary digits in group of 3 starting from the right, okay? So here you have to note here, you have to be very careful. So what we do is, if I want to convert back from this binary to octal, how do I convert? So we'll start from right and I will group all the bits in 3. So the first 3 bits is this, right? 1 0 1. So that is my first group. Then the next group is what? 0 1. Only I have 0 1, right? 0 1 is there. But you have told me to group in 3. So I have a space left. So what will I add here? I will add a simple 0. Because adding or removing a 0 doesn't make a difference. I have explained, right? So we add a 0. So these are my 3-bit equivalent octals, okay, of binary representation. So now I can simply convert this into octal back. So what is 0 1 0 in octal? 0 1 0 in octal is 2. So this will be 2. And what is 1 0 1 in octal? 1 0 1 in octal is 5. So I get back 5. So I have given you example here. You can solve the same example, right? You start from the right. Remember, don't start from the left. You will start from the right. So you start from the right. 1 0 1, this is the first group and this is the second group, 1 0 1. So it becomes 5 5 in octal. Okay, very simple. So like here the same, like I've given you a question, you can solve this question. You have to convert this binary representation in octal. So you will start from the right and you will group in 3 bits. So this is 1 0 0. This is the first group and the next group is 1. I have 2 space left, so I will append zeros here, right? This is the second group, this is the first group. So it is simply 1 and 1, right? So 0 1 1 is represented as 1 and this is also represented as 1. So this will be 1 1 in octal. So this octal will be equals to 1 0 0 1 in binary. Okay, this will be the octal equivalent of 1 0 0 2. Very simple, straightforward. And same for hexadecimal. In hexadecimal, what happens is, now instead of grouping in 3 bits, I group in 4 bits. Okay, that is the only difference, because hexadecimal has 16 digits. Octal had 3 digits. 2 raised to power 3 is 8 digits, right? Sorry, I told you wrong. Octal had 8 digits, so 2 raised to power 3 is 8. So that's why I needed 3 bits. Hexadecimal has 16 digits. 2 raised to power 4 is 16. That's why I will require 4 bits. And you might have a question, why do we use hexadecimal? In computers, once we'll study the floating point representation, there we'll see we have 32-bit numbers. To write down 32-bit numbers in this here, right, it is very, very difficult. Okay, so that's why we represent those numbers in hexadecimal for easier understanding. Once you will get to floating point representation, there we will understand the significance of hexadecimal representation. Okay, so conversion from hexadecimal to binary number system. What we do? Same procedure. Just here we will convert each digit in 4-bit binary equivalent. Like again the same thing, right? 0 is represented as 000, 0001, then 0010, 0011, 0100, 0101, 0110, 0111, and then this like this, right? It will go on. This will be 0, this will be 1, and it will go on, right? It will go on till what? 1111. And what is 1111? It is F simply. Okay, so I hope you can do this. So this one, right, how can I represent 4-digit equivalent format? Its equivalent format will be 0001, and its 4-digit equivalent format A, right? A is basically 10. How do I represent 10 in decimal to binary? You can do it, right? It is simply 1010. I hope you can do. Okay, so this is how we convert. And again the same concept follows here as well, that we will omit the MSB zeros. So we'll omit those. Reason has been explained in the previous slide. Okay, so again, if you convert it back, you can convert it back. Same procedure. From the right, you will start from the right. You will make a group of 4 and not 3 this time, and then you can convert it back to your hexadecimal from binary. Okay, now how do I convert from decimal number system? Okay, so if I have this number, a decimal number, okay, and I want to write it in binary, how do I do it? Okay, this is the standard method. There is another method that I will tell just in a bit. Standard method is just divide it by the B. What is B? B is the base. B is the base simply. Repeatedly, and note down the remainders until your remainder is lower than the base. So not lower than the base, sorry, until your quotient is lower than the base. Okay, you reach till your quotient is lower than the base. What do I mean? So here I want to represent number 18 in binary. How will I represent this? So this will be, I will keep on divide by the base. So I want to get to this base, right? Convert to this base 2. So I will keep on dividing by 2. Okay, so first if I divide by 2, this will be 9. And what is the remainder here? Remainder will be 0, because I am directly dividing. 2 into 9 is 18 only. So then again I divide by 2, 9. If I divide by 2, 9, right? The quotient will be 4. Okay, the remainder will be 1. Because 4 times 2 is 8, and plus 1 is the extra part that is remaining. Then again I will divide by 2. This will be 2. Again the remainder will be 0. Then again I will divide by 2. This will be again remainder 0. This will be 1. Now I observe that I cannot divide this further, right? Because my quotient is lower than the base itself. So I will stop here. And what I will do is, I will start from this one and I will do an arrow. So my equivalent binary conversion of 18 will start from this one and all the digits after this. So it will be 10010. This will be my equivalent binary conversion of 18. Okay, and no, here you cannot ignore the rightmost zeros. Why? Is 90 and 900 both are same numbers? No, right? A extra 0 represents something, but here, right, extra 0 doesn't represent anything, but on the right hand side it represents. If there is no point, if there is some point, that is other discussion. Okay, so I hope you understood. We cannot omit the zeros here. Zeros are important. Okay, same concept we can follow for octal. Octal again is the same number. If I want to represent in octal, our base will become 8. So I will start with division by 8. If I start dividing by 8, this will be 2 times 8 is 16, and the remainder will be 2. Okay, now my quotient is lower than the base, so I will stop here. So I will just note down the numbers. It will be 2. So 2 in octal is actually 18 in base. Can you confirm it? Yes, you can. You can always confirm it. How? You can do the back conversion, right? Octal to decimal. How do you convert octal to decimal? we write like this, right? 2 into 8 raised to power 0, the 0th position bit, and what is the bit? 2, plus 2 into 8 raised to power 1. So what am I getting? 16 plus 2, that is 18 only. So I confirmed that whatever I converted, it is correct. Now if you want to convert in hexadecimal, how do you convert in hexadecimal? I will divide by 16. Okay, if I divide by 16, I am observing that my this divisor, right, is greater than my base. Obviously I will divide, I can divide. What will be the quotient? Quotient will be 1. If I do quotient 1, remainder will be 2. Now what will be the hexadecimal representation? I will start from here and end here. Why? Because my quotient is lower than the base. Okay, so this will be 1 2 in hexadecimal will be equals to 1 8 in decimal. So this is what, again I can confirm, right? This is 2 into 16 raised to power 0 plus 1 into 16 raised to power 1. So this will be 16 plus 2, again I get back the same value 18, which is correct. So I am back confirming that whether I have converted it correctly or not. If I convert this hexadecimal to decimal, okay, so I have converted decimal to hexadecimal. Now I convert back to hexadecimal to decimal to check whether I have converted it correctly or not. Okay, so this is for integers. If I have integers, now what about fractions? If I have fractions, how will I convert my numbers? So first we'll learn how to convert numbers from decimal to other binary formats. Then I will do the reverse. Okay, sorry, other number systems, from decimal to other number systems. From number system to decimal, and then I will talk about the reverse. Okay, so the main step is we have to multiply each digit after the decimal by the base raised to power corresponding negative power. What do I mean by this? So let's take this example, right? If I have this fraction 0.001, generally if I had 101, okay, in binary, how you converted it? What you should do, this was the position 0, this was the position 1, this was the position 2. So you used to place this bit, okay, here 1, multiply by the base raised to power the bit position, that is 0. And then you would have continued, right? Then you would have continued this bit 0 times the bit position to base to the power bit position, that is 1, plus 1 times base to the power bit position, that is 2. You would have continued like this. But now the difference is there is a point here, right? 0.101. Now if there is a 0.101, what is the bit position? If this was plus 1, sorry, if this was 0 and before this it was plus 1, what can be the bit position? It will be minus 1, right? This bit position will be minus 1. Okay, because if I'm coming from left to right, I'm reducing by 1, right? If I'm coming from left to right, I'm reducing by 1. This was 1, then it becomes 0. So this intuitively it becomes minus 1. So the bit position here is minus 1, and it has a significance. I will talk about that. This bit position will be minus 2. This bit position will be minus 3. Okay. So here, can you convert it back? Now, same procedure I will follow. We just follow the same procedure, only that I write this bit digit here 1 times the base raised to power the bit position, that is minus 1. Bit position is minus 1, plus again this bit I will write here 0 multiplied by the base raised to power the bit position, that is minus 2, plus this is 1 multiplied by the base raised to power the bit position, that is minus 3. So exactly that is what we're doing here, right? Same thing only we're doing. So it will be 0.625. In decimal it will be 0.625. I am following same procedure. I am not teaching you something new. Whatever I've taught you, that only we are using. Okay. So again, if I want to convert into octal, how will I do? Same procedure. You write the bit here. Okay. Then multiply base raised to power bit position. So what is this bit position? This is minus 1. So this will be minus 2. So that is what is written over here, right? 7 into 8 raised to power minus 2. Again, I write the bit. Then I multiply with the base raised to power the bit position is minus 1. So it will be 8 raised to power minus 1. 6 into 8 raised to power minus 1. So like that you can simply calculate all these things. Okay, you can do. Hexadecimal also same rule. Nothing changes. Okay. So what about converting fractions from decimal to binary? Okay, what about the other reverse process, right? If I want to convert from decimal to binary, then how can I do it? So this method you have to just focus a bit. Here bit of tricky thing comes. Nothing tricky, but just you have to focus a bit. Okay. So if I want to, let's say, convert 0.75 into binary. How will I convert? So previously what we used to do is we used to divide the number by the base, right? Now, as it is a fraction, we will multiply by the base. We will not divide by the base, we will multiply by the fractional part by the base. Actually, this is 2 here because this is binary, but a general rule is we will multiply by the base. Then I will store the integer part, then I will repeat until the fraction goes to 0. What do I mean by this? Let me give you an example. So I will multiply, I told you, right? I will multiply this is the fractional part. Fractional part meaning the digits that is after point, that is the fractional part, right? So this is 0.75, this is the only number they have given me, it is completely fractional, so I will multiply this whole number by 2. If I multiply this whole number by 2, what is the result? Result is 1.50, right? 1.50. I get 1.50. Okay, what I will do is I will cross mark this one and I will store it here 1. Okay, I will store this one here. I store the digits before point. I store the digits before point. Then again I ignore this one. This is again a fraction, that is 0.5. I ignore this one, it is again a fraction, that is 0.5. So again I will repeat the same process. I will multiply by 2. If I multiply by 2, I get what? This will be 1.00. So if I multiply 1.00, again I will cross mark this 1 and I will store this 1 here, right? I just store whatever digit that is before the point. I store that here. Okay, we'll go through more examples, you'll understand. And I observe that I'm getting a 0, 0. As soon as I get 0, 0, right, I will stop. Why? Because if you multiply this by 2, right, it will be 0, 0 only. It will always give you 0, 0 only. So we stop. Okay. So now what will be the flow of the numbers? The flow, that this is very important. Please listen to me carefully. The flow of the numbers will be from top to bottom. Previously, when I was doing doing it for integers, it was from bottom to top. But here the flow of the numbers, even though both are same here, it will be from top to bottom. That much you have to be careful about. So the binary conversion of 0.75 will be 0.112. Now can we confirm this? Yes, of course we can confirm this. If I back convert this, right, into decimal again. So what is the bit position here? That is -1. And what is the bit position here? -2. So this is 0.5 plus 0.25. So finally it comes back to be 0.75. Hence our conversion was correct. Okay, everything was correct. So let's now solve an example. This will clear your minds more. Okay, so if I have a number, if I want to convert this into binary, how will I convert it? First I will separate it out. I will separate in 2 parts. One will be the integer part, other will be the fractional part. Integer and fractional. So what is the integer? Integer is 76. Fractional is 0.11. Okay. So for integers, I have told you the method. What is the method? Simply, you have to keep on dividing by 2 until your quotient becomes lower than your base. So I will keep on divide by 2 only. Okay, so if I divide this by 2, this will be simply 38. Here the remainder will be simply 0. Okay, again if I divide this by 2, this will be 19. Here again the remainder will be 0. Again if I divide by 2, this will be 9. Here the remainder will be 1. Again if I divide by 2, this will be 4. Remainder here will be 1. Again if I divide by 2, this will be 0 again. Remainder will be 0 again. Okay, I need to give one more. And again if I divide by 2, remainder will be again 0 and this will be 1 simply. Okay, so again I can what flow I will go? I will start from here and then I will end here, right? Flow is very important, right? What about the fractional part? Fractional part is here, right? For fractional part you have to keep on multiplying 2. So I will multiply this by 2. What do I get? I get 0.22 and I will note down the part that is just before the fraction, right? This 0 I will note down. I will cross mark this 0 and I will note this down here. Okay, then again I will multiply this by 2. If I multiply this by 2, I get 0.44. Again I cross mark this 0, I note this down. Again I multiply by 2. Okay, I get 0.88. Again I note this 0 down, and then again I multiply by 2. Don't forget to cross it mark. So this is what? This is 1.76. Okay, this is 1.76. So 1.76. I will again cross mark this 1 down, and again I will note down a 0 over here. Okay, and then again I will multiply by 2. Okay, and this will go on till infinity. Why I will explain just in a bit, just hold on. Or not infinity, actually you will get to a precision. If it is irrational number, right, it will go on till infinity. So this will be, again I will multiply this by 2. This I will get as 0.52, 1.52. This will not be 0, right? Here this will be 1 because I cross marked a 1 over here. So again this also will be a 1 because I am cross marking a 1. Again I will multiply by 2. This will be 1.04. Again I will cross this mark out and this will be 1. So what I am observing is I am very close to 0, right? I am very close to 0. After this many iterations, I am reaching very close to 0. When should I stop actually? I should actually stop at 0. Exactly, this becomes 0. But I am doing so many iterations, but I am not getting 0. So I will stop at a reasonable point when I am near 0. And what is the significance? I will explain. What if I didn't stop and went on? That also I will explain. Okay. So currently what number I am getting? I will start from the top for the fractional part and go on till the bottom. Okay. From here I will start and then totally end. Okay. This is the cycle. So what will be my binary equivalent of 76.11? 76.11 binary equivalent of 76.11. The binary equivalent of 76.11 is the integer part is 1001100. 1001100. Okay, and no, you cannot ignore these zeros. Okay, 0.000111. 0000111. Again, you cannot ignore these zeros. Why you cannot ignore these zeros? Can you ignore this 0.9 and 0.09? No, right? You cannot. You cannot ignore these zeros. So obviously you cannot ignore these zeros and these zeros. But yes, you cannot ignore zeros here and ignore zeros here. Okay. But this will be not exactly equal. This will be almost equal. Why this will be almost equal? If I do the back conversion, right? I will see I'm not getting this value exactly. So I will do the back calculation. What is the bit position here? This is 1, 2, 3, 4, 5, 6, right? So this will be 2 raised to 1 into 2 raised to power 6 plus this bit position is 3. 1 into 2 raised to power 3 plus 1 into 2 raised to power 2. Okay. Plus, what is the bit position here? Minus 1, minus 2, minus 3, minus 4. So 1 into 2 raised to power minus 4 plus 1, just the bit after that and just the bit after that again. So if I put this value in the calculator, right? If I just simply put this, so this will be 64 plus 8 plus 4. Okay. So this will be 1276. This is fine. The integer part will be fine, but the decimal part will have a problem. So if I do the calculation in the decimal part, right? 2 raised to power 4, 2 raised to power 4 plus 2 raised to power 5 plus 2 raised to power 6. It will be 1.09375, which is almost equal, but not exactly equals to 0.11. So that was the problem, right? Because we didn't stop at 0, we are not able to get to 0.11. So now what we will understand is how can I convert fractions from decimal to any number system. So it should be any number system. Okay, so like what we have been doing right now. So currently, to convert to binary, I was just multiplying the fractional part by 2. Okay, and I was noting the integer part. Okay, the non-fraction part, the part before point. Okay, so same thing I will do. I was multiplying by 2. What is 2? 2 is actually the base of the system, right? Number system. So if I want to convert into octal, I will just multiply by 8. If I want to convert into hexadecimal, I will just multiply by 16. Okay, so with the example, we will understand this. So if I want to convert 0.3 into binary system, okay, how will I convert? So let's to binary, octal and hexadecimal. So let's do for the case 1 for binary. Okay, for binary, how do I convert it? So obviously I need to multiply by 2. Okay, multiply this by 2. For this I will require space. Actually, we'll see why we will require space. So I get 0.6. I will note down the integer part, that is 0 here. Okay, and then again I will multiply by 2. Again I will note down the integer part, that is 1.2. Okay, again I will cross mark the integer part, and this will not be 0, this will be 1. Integer part is 1 now. Again I will multiply this by 2. So I will get 0.4. So again I will cross mark the integer part, I will note down the integer part, then again I will multiply by 2. So I will get 0.8. Again I will note down the integer part, that is 0. Again I will do the cross mark 2. I will note down the 1.6. So actually what is happening, this will go on till many times. I have to observe a repeating pattern. So again I cross mark this and I get a 0 here. Now what do I observe is, if I multiply this by 2, right? What is this? This is, I have cross marked the 6. This is 6, right? I got 6 here actually. I got a 6 previously as well here. Okay, so what is happening actually, after this, right, everything will just repeat. So first time I got a 0. After this, after multiplying this by 2, I got a 1, right? So same thing will happen. Again I will multiply by 2, I will get a 1. You can do it by yourself. You will confirm that you will get a 1 after this, right? This integer part. So what is happening after this, right? Everything will just repeat. These bits will just repeat. You can do it for yourself. You will see it is repeating. So this will be what? So my 0.3 in decimal will be 0.011100, and this will just repeat. Okay, like this. Again 1000, again 1000, and so on. It will keep on repeating. You will never be able to end it. What are these numbers called actually? So this number in binary number system is like a irrotational number, right? It's never ending. It is never ending. Okay, so, or I exactly don't remember what are these called. Okay, don't like come in the comment section and tell me that no, these are not called irrotational. I don't remember exactly what are the never ending numbers called. So like here, this will be equals to what? How do we represent any repeating pattern in number system? So what we do is, this pattern, right, this 1000 is repeating. So what I do, I write 100 over here, and then I make a bar over the 100, as this pattern is repeating. That's why I make a bar. Okay, so this is equals to this value in the binary number system. Now like what happens, the more points I will take, the more values I will take after the point, the more precise I will be. I will not ever be able to exactly get 0.3. I will never be able to get exactly 0.3 in the binary number system. So that is the drawback of this. So let's do the same for octal number system. So in octal number system, how will I solve? In octal number system, I will multiply by the base. What is the base now? Base is now 8. So if I multiply by the base, this will be 2.4, and again I will cross mark the integer part. I will note down the integer part, then again I will multiply by base. This will be 3.2. Again I will note down the integer part, again I will multiply by base. This will be 1.6. 8, 4.8. Actually this should have been 4.8. This is 4. I get this is 0.8 into 0.8, right? 0.8 into 0.8 is 6.4 actually. So I get 6.4. And what do I observe? I observe that this 4, right, was actually here, right, also. So again I observe a repeating pattern. So everything after this 2, right, will just repeat. Same thing. So 0.3 in decimal will be equals to 0.23146. And what is repeating after this, right? After this everything is repeating, like this 0.4 times 8. Here also same thing is happening, right? After this 0.4 I will again multiply by 8. So this whole thing is repeating. You can check and confirm for yourself. You will get back the same result in octal. What about hexadecimal? Hexadecimal, like same thing only will happen. That is, this is 0.3. Again I will multiply by its own base, that is 16. So this will give me 4.8. This will be 4. Now one thing, like I think you will have a doubt that what if whatever number I get here, right, that is greater than the base of the number system. Because here, right, I was multiplying by 2. What if I get a number that is greater than the base, like 2? Is that possible? That is actually never possible. Why? Because you're always taking a fraction. A fraction of what? You're multiplying the base of the system with a fraction. So fraction means a number that is less than 1. So you will always get a number after multiplying with the base that is less than the base itself. So you can never ever get a number that is more than the base. It is not possible. That's why I think you will have this doubt that what if I get a number that is more than the base? That will be invalid, but that is not possible. By program, that is not possible. Okay. So yeah, that's why that is a not defined case. So 4.8 into 0.8, then again I will multiply with the base 16. So this is 0.8 into 16, that is 4 by 5 into 16, or how can I do it? This will be okay, 8, 80 and 48. Yeah, this will be 12.8. So I get back 8 again, right here. This will be 12. I get back a 8 over here. This was 8, right? So this will just repeat. This will simply just repeat. What is happening after 4? I'm getting 12. This 12 will just keep on repeating. This 12 will just keep on repeating. Now, what is 12 represented as in hexadecimal? 12 is represented as C. Correct? So this will just keep on repeating. Again, if I multiply 16, what I will get? I will again get 12.8 only. So I will keep on get 12.8 only. So my 0.3 in decimal will be equals to 0.4 will be there. Then C, this will keep on happening. So basically, this will be equals to, in hexadecimal, this will be 0.4 C bar. Okay, so that is what we get. So there is a last topic about the number representation. Is one easier way to convert from your decimal to binary. Okay, like we do the same thing only. Instead of dividing everything, right, I can use a shortcut. What is the shortcut? The shortcut is, let's say I have a number 156. One thing is, if you want to convert, this is in decimal, if you want to convert this in binary, what you do, you will divide by 2 to 2 and note down the remainders. That you can do. Another method is conversion using weights. So this 156, right, is basically what? It is basically addition of the bits on the binary multiplied by their weightage, the position that they are on. Okay, so what I can do, I can assign weights to each bit. What do I mean by this? If the bit 0 of the binary is 1, that means what is it represented in decimal? It is 2 raised to power 0 into 1, that is 1 only. If the bit 1 is 1, okay, if the position bit 1 is 1, what is the weightage in decimal? It is 2 raised to power 1. What is it? It is 2 simply. If the bit position 2 is 1, that means what is the weightage in decimal? It is 2 raised to power 2, that is 4. So that is what we do basically here. Okay, all these things are written, you can read from this. Basically what we do is, this is a shortcut method. What you do, I observe here 156. So first I will try to write the largest number that is closer to 156, that can be represented as a power of 2. Like I want to convert into binary, I will just only take for the case of binary. Okay, I will not take for the other cases. So for the power of 2, which is the closest number? 128. So I see I can write 128, right? That is the closest number. What is 128? 128 is 2 raised to power 7. Correct? 120 is 2 raised to power 7. What does this 7 means? That means bit position 7 is 1. Okay. Plus, now how much is left? After 128, how much is left? So if I add another 8 and 30. Okay. Not 30, sorry. 20. So 28 is left. After I got my 128, now 28 is left. Now what is the closest number that I can write? That is a power of 2 that is closer to 28. It is 16. So we write 16 here. Okay, I got 16. That is 2 raised to power 4. That means what does it mean? It means the fourth position of the bit binary in the binary system will be 1. Now 16 is gone. 128 is gone. How much is left? 28. 28 was left, right? 28 was left. Now I took out 16 from that. So only 12 is left. 12. How can I represent 12? I can represent 12. What is the closest 2 raised to power number that is closer to 12? 8. After 16, 8 is there, right? So 8 is there. That is 2 cube. Then what is the next number that is closest to the remaining portion? What is the remaining portion? Only 4 is remaining. That is 2 raised to power 2. So 4 is there. That is 2 raised to power 2. Okay. So without it may seem slow as I am explaining, but actually this is faster than the previous method. I just written the bits which are 1. Okay, that much I need to calculate. So bit position 7, 4, 3 and 2 will be 1. So this number can be represented if I start from the right hand side. Bit position 2 is 1. So other bits are 0. Then position 2 I come make a 1. Then 3 is 1. Then 4 is 1. And then 4 is 1. Then 5 is 0. 6 is 0. And 7 is 1. So the binary equivalent of this number, right, will simply be this. If you want to cross check, you can cross check, right? You can go back. So what you can do? This is what? This is 0, 1, 2, 3, 4, 5, 6, 7. So 7th, 2 raised to power 7 plus this is the 4th position. This is the 3rd position. This is the 2nd position. So you can simply go back. Okay. So this is a shortcut method than dividing by 2 over and over again. This is a shortcut method we will use throughout the lecture. Okay. So I hope you understood this point. We just write it in terms of weightage. So what does each position bit weightage has in the decimal number system? That is what I write. So this right, the rightmost bit will have the lowest weightage. That's why sometimes they are called as LSB, lowest weightage. That's why they are called LSB, that is least significant. They have very less significance because their value is very low. Least significance. Okay. And the bit position that is at the leftmost, right? You can observe its value is very high. Its weightage is very high in the decimal number system. So that's why it is called as the most significant bit. Most significant. Okay. And what is its weightage? Its weightage is simply 2 raised to power n minus 1 if it is in binary. If it is in some other base, you will just write that base raised to power n minus 1. N minus 1 is the position of the bit. So like you can write before point, right? This will be 1, this will be 0, this not 0, sorry, this weightage will be 2, this weightage will be 4, this weightage will be 8 and so on. It will be a multiple of 2. Okay. So like that's how you write using the conversion using weight, right? That's how you use this process. So here I have given you few examples. You can go through those and like solve for yourself. Okay. Now let's come to computers because we were on computers only. So how are numbers represented on computers? As we know, the numbers are stored and represented in binary form. In computer, everything is in zeros or ones. Okay, this information we already know. This binary representation ensures compatibility with digital logic of computer system. Why did we use 0 and 1? Because it is very easy to implement any digital logic, because digital logic only talks about 0 or 1, right? If you have studied latches, if you have studied combinational logic, if you have studied sequential, there we only did zeros and 1, and those zero digital logic are actually implemented to make computers, right? So obviously that's why binary was the go-to choice of our number system to use in computer system. But we don't understand, right, binary, so we have to convert it. So everything is in binary, every single thing. Your numbers are in binary, your characters, okay, A B C D whatever, that is also in binary. Okay, that is also in binary. There is a standard, and your floating point numbers like fractions, every single thing is in binary in computers. Okay, so binary representation of data values, all types of data with a numeric character are stored in binary formats, zeros or ones. Fixed point numbers, numbers with fixed decimal or binary point. That means that their decimal point is not variable. What do I mean by this? 1.01, this is a fixed point number. This point, right, this point is not moving. Okay, this point is not moving. Now if I write something like this, 3.56 into 10 raised to power x. Now what about the value of x? According to that value of x, this point can move, right? So this is a variable floating point, because it is a floating number, but it is variable. That's why it is called as floating point numbers, number with variable position for the decimal or binary point. So this point, right, this point can float around anywhere, any place. That's why it is called a floating point numbers. Okay, then we have characters. Characters represented using encoding standards like ASCII or EBDC. Like, just you should know this name, ASCII, okay, and EBDC. What are these? These are standards that has been defined by the world. Okay, we follow this standard. What this standard says is that this character A, right, this character A, in computers, this character A will be some combination of 1 0 0 0 0 0. Okay, some combination of 1 0. Okay, that has been defined, that is set. Ever if I write A in the computer knows that its binary equivalent is this value. Okay, I also don't remember, but its binary equivalent is this. That has been set by a standard. We follow few standards. Okay, so that's it. Like, it's just like force has unit of Newton, right? That has been set. That is a standard. This is also standard. Okay, these are predefined in the computer. Okay, these are the architecture that has been predefined in the computer. Now, like I told you, right, numbers and characters are there. Characters are there. We generally use ASCII codes or EBDC. Generally, we use a common standard, that is ASCII. Okay, and you should know the full form. That's it. For gate also, that is not that important. Okay. Now, numbers can have two things. One is fixed point, and another is floating. Fixed point, mainly we are considering integers. Mainly we are talking about integers. In fixed point, we are mainly talking about integers. Okay, and floating point, mainly we are talking about the fractional part. Okay, so in fixed point, right, there can be two numbers. One is unsigned and signed. Now, as seen from the name, what you can understand is this doesn't have any signed associated with it. It will always be positive, and this will be signed. Okay, that means it can be negative or positive. It can be negative or positive, both. Now, what is the technical definition? Now, like this definition is very simple, right? Okay, it has a sign, so it can be negative or positive. That previous one is unsigned, so it doesn't have any sign. It is always positive. That is simple. But what is the technical definition? Technical definition is the sign numbers are those numbers with which we will be performing arithmetic operations. So, we will be performing arithmetic operations with these numbers. With unsigned numbers, we actually cannot perform arithmetic numbers, because unsigned is always positive, right? I don't know whether actually originally that number was positive or negative. That's why we cannot perform the arithmetic operations. So in other language, these signed numbers sometimes are also called as arithmetic numbers. Okay, Sometimes they are also called arithmetic numbers. So that is the case over here. I hope you understand the difference between signed and unsigned numbers. So like here, same thing is written. Signed numbers allow representation of both negative and positive values. These are stored in binary with specific conventions. Because I told you, right, computer stores everything in zeros and ones. So we have to follow a specific convention for the computer to make it understand that this is a negative number and the other one is a positive number. How does the computer understand? It is a very dumb machine. Okay. So there are mainly 3 standards that we follow. Okay. For sign convention. Okay. First is sign magnitude representation. The most significant bit, MSB, is used as a sign bit. What does it mean? Basically, my number, right, magnitude of the number will be consisting of 7 bits. Okay. Or the like whatever bit they have provided. One bit will be reserved, that is the MSB will be reserved for the sign. Now, if this bit, right, if this bit is 0, that means I understand that it is a positive number. If this bit is negative, if this bit is 1, that means I understand, and computer also understand that it is a negative number. Okay. So that's just the difference, right? If this bit is 0, that means the computer understand it is a positive number. If this bit is 1, computer understand it is a negative number. Very simple to understand. And what is this? This is just the magnitude. Okay. Magnitude of the number. Let's take a, for example, 5. Okay. Plus 5. How will it be represented in 4-bit representation sign magnitude format? So if it is plus 5, the binary equivalent of 5, that is magnitude, is 101. Okay. 1101, right? Binary equivalent is not 1101. This is again, okay, sorry. Yeah, it is 101 only. 101. Yeah, it is 101. Okay. Binary equivalent is 101. Now, this is plus 5. So, and it is a 4-bit representation. So, I will write here 101. Then the final bit, what I will do, I will see if this number is positive, then I will put here 0. If this number is negative, then I will put here 1. Now, currently I can observe that this number is positive. So, I will put 0. Now, same example, but a negative number. Okay. If it is minus, so first of all, I will write the 3 bits, that is the magnitude. Magnitude will be 101. That will not change. But sign is now minus. If sign is minus, I simply put this MSB, right, equals to 1. If the MSB is 1, that means it is a negative number. That's it. Now there is a special case. What is the special case? Special case is if I have 0. 0 can have 2 representations. One is plus 0 and minus 0. Although both are same only, arithmetic operations will also come out to be same. But in this particular representation, 0 will have 2 representation. One is plus 0, one is minus 0. Both the same. So we are wasting a space basically. So how do I write plus 0? Plus 0 basically all these bits are 0. MSB is also 0. That means plus 0. If all the bits are 0 and MSB bit is 1, that means it is a minus 0. That's it. And it arithmetically it is nothing is different, but just that there is a representation of this plus 0 and minus 0. That's the only difference. Now there is another representation for sign number, that is ones complement representation. So in our full course in digital electronics, this has been covered comprehensively. So I'm not covering it comprehensively. How much of it is required for IEEE floating point representation, that much only I'm covering. Okay. If you want to get more knowledge about this sign representation, you can go through our full course. Okay. The positive number is stored in standard binary format. So like what we do is, positive number we don't change anything. Okay. If it's a ones complement, what we do, if it is plus 5, right, I will just store 101. Now this, right, this is the, let's say this is the 4-bit representation. How do I represent a number in 4 bits? So what is the binary equivalent of 5? Binary equivalent of 5 is 101. Now if I want to represent it in 4 bits, I don't want to represent it in 3 bits. What will I do? I will just add a extra 0 on the left. Does it make a difference? No. If I add a 0 here, does it make a difference? Yes. This is 2, this is 0, 2, this is 0, 0, 2, right? It doesn't make a difference. If I add 0 at the left, there is no point here, but it does make a difference if I add zeros at the right. Okay. So obviously I will just add a simple 0. It will not make any difference here. Why am I adding zeros? Because they will tell you how many bits you have to represent, right? Ones complement 4-bit representation. So you have to represent this number in 4 bits. So this is the simple if the number is positive. If the number is negative, what we do is we just simply do the not. I hope you learn, Boolean algebra, basic logic, that I will invert these bits. Whatever was the positive number, I just invert those bits. Okay. So if the positive representation of plus 5 is 0, 1, 0, 0, 1, 0, 1, then the negative representation will be just the inversion. That is minus 5 will be represented as the invert of this, that is 1, 0, 1, 0. That's it. Okay. Again, for plus 0 and minus 0, there will be two representation. Plus 0 will be just a simple conversion of 0, okay, in 4-bit representation. But minus 0, sign is negative, right? So I have to invert the positive form. So this will be inverted all once. Okay, so like that's why we shifted to a 2's complement representation. And what does 2's complement representation say? It stores the positive numbers as usual, right? It doesn't change anything. It stores the positive number as usual. But what it does is the negative numbers, it actually does a special thing. What it does, first it inverts all the bits for the positive number. Basically, for the magnitude, the binary representation, it will invert, that is 1's complement, and then it will add 1 to the result. That will be a 2's complement. Okay, that's it. Nothing fancy, nothing. Why we do this? Just to eliminate the ambiguity of 0 and plus minus 0. Okay, so let me take an example. Here I have 5, right? So what is the 2's complement representation of plus 5? For positive number, I will not change anything. So it will be simply 0, 1, 0. It will not change. But for negative number, what will happen? It is a negative number. I know it is a negative number. So first I will write the 1's complement, that is 0, 1, 0, 1. Then I will take the naught of this because it is a negative number. It will be 1, 0, 1, 0. Then what I will do? Then I will add 1 with this. If I add 1 with this, this will be 1, 0, 1, 1. So this is my 2's complement representation of the minus 5. Okay. Now, how does it eliminate the ambiguity of plus 0 and minus 0? So if I have plus 0 is very easy, right? It is simply 0, 0, 0, 0. Minus 0. For minus 0, first what we do? We write the simple binary representation of the positive number. Then I invert the numbers. So everything will be 1. Then I add 1 with it. If I add 1 with it, right, what will happen is this will become 0. This will become 1, 0, 0, 0, 0. Now, as I have told you that we are only using 4-bit representation, what our computer will do, it will just neglect this extra bit because now I have got 5 bits. But our computer will just neglect the extra bit because my computer can only store 4 bits and it will store the bits from the right. Okay, it will start from here and it will store the bits. So it will only store the 4 bits. After it will not store anything. So computer CPU will neglect this. Okay, so that's how I got that I am getting a same representation for plus 0 and minus 0. So it's just a representation, nothing else, nothing fancy. So let's do a few example, like just one example we'll do, and that should be enough. Okay, so represent 56 and minus 56 in sign, magnitude, 1's complement and 2's complement, 8-bit representation. So they will give with a number of bits. So I have to represent in 8 bits. So what about sign, magnitude? So I'll do for the part A. Plus 56. So how do I do the signs bit representation of plus 56? So what I can do, it is positive. If it is positive, I can simply write the binary conversion. What is the binary conversion? How, again, I will use the weighted binary conversion. So the biggest 2 raised to power number that I can write that is closest to 56. What is it? It is 32. 32. Then I can write that what is left. How much of it is left? 24 is left. 24, that means 16 plus 8. Okay, and nothing else is left. So this is 2 raised to power 5, 2 raised to power 4, 2 raised to power 3. Okay, so this will be like 5th bit will be, sorry, the position 5th bit will be 1. Okay, so 0th bit will be 0, 1st, 2nd and 3rd. As I come to 3rd, I see there is a 2 cube. So that means this bit will be set. Then again 4th bit will be set and 5th bit will be set. This is the, like, how many bits are this? These are 6 bits. I have to represent in 8 bits. So the remaining bit will be 0 and it is a sign magnitude. So like these are 7 bits. So I have represented the magnitude but sign will be decided by the MSB. Okay, the most significant bit. As it is positive, so I will write here 0. Sign is positive. Okay, now this is the part A. Part B is what? Minus 56, 10. Basically what we do, everything is same, right? We don't change anything. This part will be same only. This will not change. Just what will change is the MSB, because it is a negative number. That's why the MSB will be set. It will be 1. That's the only difference, nothing else. Okay, for second case, for second case, it is a, I have to show a ones complement. So if I have to do a ones complement for 8-bit representation, what do I know? For ones complement, if it is a positive number, I just directly write the binary binary conversion of it. So the binary conversion is this only, right? 111000 111000, but I have to represent in 8 bits. So I will just add extra zeros before the 111, right? So I will add the extra zeros here, this 0, this 0. So total I get 8 bits, and this is the ones complement representation of plus 56. Now what about minus 56? So for minus 56, what do I need to do? It's very simple, right? Whatever is the positive number, that I will write 001110000, 8-bit representation I will write. Then I will simply invert. I will simply invert it because it is a negative number. I have to invert. So it will be 110000111. Okay, that will be the ones complement representation of minus 56. What is the twos complement? For positive, nothing will change. It will be same only. So I can directly copy paste. We can directly copy paste the ones complement representation. For negative, just one step will be added. The first step is common, that is, I will write the positive ones complement representation of 56. Then I will invert. Then what I will do? Then I will simply add an extra 1. So this will be 11001000. Okay, that's it. This is the twos complement representation of minus 56. Okay, so what if I want to do the back calculation? What if I want to come from the twos complement representation to my decimal system? How do I do it? So for sign magnitude, it is very simple, right? For sign magnitude, it is very simple. First, I check all the bits, okay, except the MSB. I treat as unsigned. I convert from binary to decimal, and then I check the MSB. If the MSB is 0, then it will be a positive number. If the MSB is 1, it will be a negative number. Okay, let's check the example here. Let's check the same example, right? This one. I did the sign representation, right? I'll just copy paste this. I got a number here, and I will just accept the MSB. I will check all the other bits. Now if I check all the other bits, the decimal conversion will be simply 56. Okay, and this MSB is 0, that means it is a plus 56. Now if I take the negative number, again I will take all the numbers except the MSB, and its decimal conversion is 56, and I observe that the MSB is 1. If the MSB is 1, that means it is a negative number, so it will be minus 56. That's it. Okay, that's simple. For ones complement, how will I check? Now here, right, you have to be careful of it. Okay, generally either they will tell you the sign, like either before, like they will just give you this number. Okay, two things can happen here. First thing is, they will give you this binary number, and they will tell you that it is a positive or negative number. They will tell you in the question. And the second thing is they will not tell you. Okay, and by default second case always happens. They never tell you that whether this number is positive or negative in the question. How do you identify whether this number is positive or negative? So what you do is, you actually, even though it is a 8-bit representation, 1's complement 8-bit representation, it is by default assumed that this first bit will be signed bit, just like the previous case. First bit will be signed bit. Okay, so if the first bit is signed bit, what you do is, you check the first bit. You check the first bit, it is 0. If it is 0, it will be a positive number. So you will do the direct conversion of this whole remaining 7 bits to decimal. Okay, I will do the direct conversion of this whole remaining bits to decimal. Okay, so what will be the direct conversion? Direct conversion will be simply 56. So I get my 56, get back my 56. Now, if I take the negative, right? If I take the negative number, how will I choose here? So here, what I do is, actually I should neglect this bit. Okay, I should only take this 7 bits. Okay, and this bit is 1. Now why did I delete 1 and put a yellow one? That is that is a different perspective. You don't need to go into that, but for now just understand that this is actually like minus 56 only. How will I get minus 56? First thing you observe is that I am getting a 1 at MSB. If the MSB is 1, as written in the steps, if the MSB is 1, you will just simply do the bitwise NOT of all the other bits. Then I will do the conversion from binary to decimal. So first I will NOT this bits, right? If I NOT this bits, what will I get? This will be 0, 1, 1, 1, 0, 0, 0. Okay, now I will do the binary to decimal conversion. If I do the binary to decimal conversion, this comes out to be 56, but I knew from the MSB that it is a negative number, so I will add a minus sign here. Okay, so this always by default your MSB will tell you the sign of the number. Okay, by default it always happens. Let's do the 2's complement. In 2's complement everything is same, just one extra step gets added. Okay, so what we do is, first I check the MSB again, this number, right? This number I can take. This number I can take. I check the MSB. MSB is 0. MSB is 0. That means it is a positive number. I don't need to do anything. Direct binary to decimal conversion. What is the decimal conversion? It is simply 56. Decimal conversion is 56. Now, if it is a negative number, what will I do? So first of all, I will just cross mark the MSB and I will write here 1. 1 represents that it is a negative number. Okay, I see a 1 in the MSB. As soon as I see the 1 in the MSB, what I will do? First I will invert all the other remaining bits. Then again I will add a 1. So I will invert all the bits. It will be 0, 1, 1, 0, 1, 1, 1. Okay, then I will add a 1. So if I add a 1, I get 0, 1, 1, 1, 0, 0. Okay, and this I will convert it. This is a binary representation of my actual decimal number. What is this? This is simply 56, right? So I will write here 56. But I knew from this MSB that it is a negative number, so I will write here minus. So that is what they are doing in this particular thing. You can go through this. I am not going too much in depth because this is not that important. Just wanted to say to you how we are finding out the values. So here, let's do this question. With this question, everything will be clear. A number n is represented in 8-bit signed binary format. Okay, it is a 8-bit signed binary format. What does it mean? Basically, it's MSB talks about the sign. Okay, MSB talks about the sign. Perform the following task. Given n is this, in 8-bit signed magnitude format, convert it back to its decimal equivalent. Given n is this in ones complement format, convert it back to its decimal equivalent, and if it is in twos complement format, convert it back to its decimal equivalent. Okay, so let's do it for the first one. So for the first case, my n is what? Okay, nothing is mentioned, so I will assume, like, if most cases nothing will be mentioned, so we assume that MSB is the sign bit. Okay, so given n is equals to 1001 n 10011 101 10010 110. Okay, 10010 so it is 8-bit. Now what do I observe? I will observe the MSB. MSB is 1, that means it is a negative number. If it is a negative number, I will just, first of all, I will directly convert this into, it is a signed magnitude format. It is a signed magnitude format. I just need to check the MSB and that's it. I just basically convert this back into my decimal and then I add a negative sign. So this will be what? This is 2 raised to power 1 plus 2 raised to power 2 plus 3, 4, 2 raised to power 4. So this will be simply 22. And of course, MSB is 1. So my final answer will be n is equals to minus 22 in decimal. Let's solve the second one. Second one, n value is 111001. N is 111001. Correct? 111001. Again, assumption is my MSB will be the sign bit. Okay, so I observe that it is a negative number, and if MSB is negative, that means I will simply first do the complement of this. It is a ones complement for representation, right? So the complement of this will be 0010110. Then I will convert it back to my decimal. So it is 2 raised to power 1 plus 2 square plus 2 raised to power 4 equals to 22. So this is 22. Now I know this is a negative number, so my final n will be equals to minus 22 in decimal format. Okay, let's talk for the third case. So in the third case, my n is equals to 1110110 1110110, right? 1110110. So again, MSB is 1, so it is a negative number. So into its complement, just one extra step gets added, that is after complement, right? If it is a negative number, so I have to complement this first. So the complement this will be 0010101. Okay, then what I do for 2's complement, I have to add extra 1. So if I add extra 1, this will be 0010110. Okay, 110. I get the same value only, that is 2 raised to power 1 plus 2 square plus 2 raised to power 4. That is equals to 22, and I know it is a negative number, so my n comes on to be minus 22 only. So you can observe that different representations will have different values, okay, in binary, but finally ultimately I'm getting the same value in decimal. Okay, so that is the basic point that I wanted to discuss. So like summary is here, you can go through the summary, you can read all this. Okay, so like why we like introduced an extra 2's complement, you might have a bit of doubt, is to negate the ambiguity of minus 0 and plus 0. That's why we introduced a 2's complement. I told you, right? And how we remove the ambiguity as well. From here I told you at the starting of the 2's complement. Okay, so why 2's complement is preferred? Because it has unique zero representation, efficient arithmetic operations without the needing of any separate hardware. Okay, and it simplifies logic detection. Okay, so like don't need to go into the technicalities because this is not that important. Like all this difference will be there, just you can go through, read once, that's it. For other non-tech which are like AJ examinations, this information can be useful. And I told you, right, for character representation we use ASCII or EBC, DIC, mainly we use ASCII. So you should just know the full form of ASCII. That's enough. That's enough. How, like you can observe, right? It is a standard. So A in computers, it represented as 010001. Okay. It is a standard, and small a is represented as this. Every character has a binary unique code associated with it. Just like every person has a unique name, every character has a unique binary code associated with it in the computer. So that's it basically for this lecture. This is just an introduction, basic lecture. From the next lecture onwards, we'll come to our floating point representation. Okay. So thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone and welcome back to PrepFusion. So today we'll start the lecture 2 of our number representation chapter, which is included in both COA and digital electronics. So this is included for both these subjects. So both, like, who are preparing these subjects, both of them can watch. Obviously placement people also should watch this video. Okay. So today what we learn, we'll continue like yesterday, like in the previous lecture, what we learned about the representation of numbers, different representation of numbers. Okay, what are different base. So today we'll learn about a very specific representation, that is floating point representation. Okay, there are two types of floating point representation. One is a conventional. Okay, after that we made a standard. All the scientists, all those people made a standard that this is the standard, this is what we follow. That has a rule, so that rule I will explain, and that is known as IEEE 754 floating point representation. It is a standard, IEEE 754 standard. Okay, so everything is fixed here. So in this lecture, right, at the starting it may feel like you are not able to understand few things. Okay, just have patience with me, and trust me, at the end of the lecture you will understand everything perfectly. Okay, and you will understand everything, like even though if you have studied this topic previously, right, you will gain some new knowledge after studying from here. Okay, so another point is, if you are enjoying, if you are liking the concepts, all those things, please do hit the like button. That really makes us, like, appreciates to make more video on YouTube. Okay, so those were few demands. So let's start. Why do we need floating point representation? Like what is floating point representation? So floating point representation is a numerical system used in computing to represent very large numbers or very small fractions very efficiently. How it happens, we'll understand today is that lecture. Okay, so overcoming the limitations of fixed point representation. So what are the limitations of fixed point representation? So what is fixed point representation? Fixed point representation means the position of the point is fixed. Let me say that in a computer, in a particular computer, the position of the point will be here. Okay, let me take an example. I have a number, let's say 10.01. Now I cannot vary this point. This point will be here. Okay. Like before the point I will have 2 digits, and after the point I will have 2 digits. That is fixed. Okay, this point will not go. So if I have a number like 1.01, how will I write this in this particular computer? I will write this like this, 01.01, because appending a 0 at the left doesn't change anything. Okay, if I have a number like 1.1, how will I write it? I will write 10110. So here actually the point is fixed. The point doesn't move, right? The position of the point is always fixed. That's why the name fixed point representation. But in floating point representation, what will happen? In floating point representation, what I can do is this 1.01, right? This point need to be presented. Like my computer can represent this, and it can represent this, and it can represent this as well. If let's say my computer can represent 4 digits, okay, 4 digits only, so it can represent this. Okay, so what will I do? I will just add a 0, because my computer should always show 4 digits. So to show 4 digits, it represents like this. It can also represent this, right? How will it represent? It will represent like this, and it can also represent this as well. What happened? Previously, every time before and after point, I had 2 digits. Point was fixed, position of point was fixed, but here the point moved. The point moved here. Okay, so after the point I had 3 digits. So the precision increased, right? Now I can measure 0.01. I can represent 0.01. In fixed point representation, I can only represent 0.01 sorry, I can only represent 0.01 and 0.02. So in between this number, right, between 0.01 and 0.02, I cannot represent anything. I cannot represent. But this I am able to with floating point representation. That's why we are using floating point representation, and that is what is written over here. So however, they have limited range. Very large numbers or small fractions cannot be represented together. Okay, either you can choose only one thing. Either you can represent very large numbers. How can I represent very large numbers? Let's say my computer can only show 4 digits. So what I will do, if I want to represent very large numbers, right, I will put the point 1, 2, 3 at the end. So now I can represent very large numbers, right? My computer can show all large numbers. But can I represent this 0.001? No, because my point is fixed, right? The position of the point is fixed. To the left of the point, there should be 4 digits always. That is a fixed point representation. Okay, so position of point is fixed. So that's why I can represent large numbers, but I cannot represent very small numbers. But let's take the other way. Okay, so if I choose to represent my point like this, that after point there should be 3 digits. I can at max represent 9.999. Can I represent 1, 2, 3 or something? No, I cannot. If the point is fixed. Okay, so that's why this fixed point representation has very limited range. Now, floating point allows the binary point to float, enabling representation of much larger. I have explained how it does that. So like here I have given you example for a fixed point, right? Fixed point representation. If I have 16 bits, the range will be between this minus, like if it is an integer, the range will be minus 32,768 to plus 32,767. That will be the range. Okay, for a fixed point representation. But for floating point representation, the range will be huge. I'll show you what will the range, how much smaller can I represent, how much larger can I represent. Okay, those will understand. So that was the limitation. And obviously, if you want to increase the range, right, what you have to do? You have to increase the number of bits. Then the range will be increased. But we have limited space. So that's why instead of increasing the number of bits, what we do? We use floating point representation to increase the range. So like last analogy about floating point and fixed point representation, then I will totally shift to the floating point representation. So like you can think your simple fixed point representation like a single scale. You have a scale, right? You have a scale which at minimum can measure mm, right? It is a linear scale. It is a linear scale which can only measure mm. The minimum value it can measure is mm. But if I have a telescope, right? If I have a telescope, where what I can do is I can adjust the zoom, right? I can turn the knob, and that knob is actually non-linear. That is not linear. So it zooms exponentially. If you know a bit about telescopes can zoom so much that we can see the stars very close, like in a good resolution, and it can zoom out so much that it can see the small things as well. Okay, zoom in and zoom out. Everything is there, right? It can see very large distances. It can see very small distances, like in our cells. Those things also it can see. There is a non-linear scale over there that does. Okay, we don't want to go into the technicalities, but I hope you get the point. So now we'll understand how are floating point numbers represented. Don't worry if you don't understand this. Don't worry, we'll solve examples through there. We'll understand. But for now, just have an idea. Okay, in your brain. Get in your head. Okay, floating point number is represented like this. What is this? I also don't know. I will explain. Don't worry. Okay, I also don't know. We together will figure this one out. Okay, so first let's understand few notations. Okay, so this term I think you know. What is this? -1 raised to power s. What is this s? This s is the sign bit that I discussed in the previous lecture, right? So if I told you previously, if the sign bit is 0, that means it is a positive number. If the sign bit is 1, that means it will be a negative number. So this -1 raised to power s is just for the sign. Okay, just for the sign. So if s is 0, then -1 raised to power 0 will be simply 1. So it is positive. If s is 1, -1 raised to power 1 is simply -1. So it is negative, as I explained in the previous lecture. So this thing you don't have to worry, right? This is very simple. So in our floating point representation as well, what we do is we keep a single bit reserved. MSB is reserved for the sign bit. That hasn't changed. Okay, from previously also we are doing the same. Here also we are doing the same. We're keeping the MSB for the sign bit. That thing is sorted. Now let's come to the other two portions. One is this exponent, other one is this mantissa. Okay. So mantissa is the fractional part and exponent is the exponent. Okay. So slowly we'll understand. So let me take an example. Okay. Let me take an example. So if I have a number, as 3.5. Okay. Now mantissa, they are telling that mantissa is the fractional part of the number. What I will do is, I just want the fractional part. But if I just take the fractional part 5, then this information of the whole number will be gone, right? I won't be able to store the 3. Information of 3 is gone. So the people were very smart. So what they did was they converted this whole number into a fraction. How did it? So what they did is, you can write 3.5 equals to 0.35 into 10 raised to power minus 1. Okay, like this you can write. Now, is this a fractional part? Yes. Okay, are these two same? Yes. Am I losing out any information if I store 0.35? No. Okay, because I will store this information as well. That will come to later on. But if I store 0.35, I am not losing any information about the number, right? Previously I told, if I just store the fractional part, that is 0.5, I am losing out information. So I have to keep all the information. So I convert it in this form. This has a name. I will come to it later on. Don't worry about this right now. Okay. So I just want to store this. So this is the mantissa. Basically. Okay. This is the mantissa. Now, this is in decimal number system, right? Because you're accustomed to see in decimal number system. So I took an example of decimal number system. But obviously we're talking in computer language. So everything should be in binary number system. So if everything is binary number system, the numbers will also be in binary. So instead of this example, now I'll choose a binary number. Let me choose a 1.0111. Okay. This is the number. Now what I will do is, I have to convert, this is in binary, so I have to only choose the fractional number. Again, if I choose only the fractional part, I am losing out information. So I have to put everything in the fraction. So what I will do is, I will put everything in the fraction. Okay. So here, okay, previously I think I did something wrong. This was 3.5, right? I did 0.35. Actually, it was wrong. Sorry. This should be 10 raised to power 1. Okay, my mistake. This should be 10 raised to power 1. Previously, I did that wrong. So now I shifted this point twice left. So what should be the multiplication here? What should be the multiplication? When I did this, right, 3.5 moved on the left. What was the multiplication? This was 0.35 only, as I move everything on the right hand side of the point, multiplied by 10 raised to power 1. So what is this 10 actually? This 10 is the base of that number system. It was decimal. So what should I multiply here? I should multiply 2. How many points? Like here I moved 1 point to the left, that's why this is 1. Here I moved how many points to the left? 2. So that's why this will be 2. Okay, so I'll delete this, we don't have space. So this will be 2. Are these same? Yes, both of these are same. Both these doesn't change. Both of these are same only. Okay, I have shown you with the example of the decimal. So you can always revert back to the decimal number system if you ever get stuck in binary number system. Okay, so this part is done, right? Now I am storing, this is the mantissa. This is the mantissa. Now you might have a question, sir, you are normalizing it like this, but what if I normalized it like this? 0.011011. What if I shifted this point not twice but thrice on the left? That is also possible, right? Just what will change? This 2 and 3 will change. You will say, sir, I will store this mantissa and I will store this 3. Then also I am able to recover all the information about the particular number. I will say you are correct. But I can also do this, right? 0.0011011 into 2 raised to power 4, and I can go on, right? So there has to be a standard. So that you don't get confused, I also don't get confused, and you don't kill your brain by just thinking about this, because you have other things to think about. Okay, so we have a standard. This particular conversion, right, whatever I have done here, this has a name. From here to here I did something. Okay, the name is normalization. What I did is I normalized this particular number. Now there are two types of normalization, that is explicit and implicit. What are explicit and implicit normalization? That I will come to. Okay, later on. For now, just understand this. From this here to here I did normalization, and what information I will store? I will store this is the mantissa, and I will store this exponent. This is the mantissa and this is the exponent. Okay, if I know these two information, will I be able to recover my previous number? Yes, if I do this back calculation, I will be able to recover. So what things are stored in floating point representation? Please listen to me carefully. What things are stored in floating point representation? This information, yes. This information, yes. This information, no. This information is not stored. Because I am in computers and I know computer only follow binary number system. So the base is inbuilt. Computer also knows, you also know that this base will be always 2. So this 2 is fixed, right? This 2 will not change. What can vary? The mantissa can vary, the exponent can vary. That's why we don't store this. This information is redundant. We already know it is a binary number system. In computers, it will be binary number system and it will not change. That's why we don't need to store this. We store the exponent, we store the mantissa, and obviously we store the sign. And with the help of these three things, we will be able to come back to our original number. Okay. So I hope you get the point. Up until now, I hope you get the point. Now let's take an example. Okay. Let's take an example. I have a 6-bit system. Sign bit is 1. Mantissa has 3 bits. Okay. It is a normalized fraction. Exponent has 2 bits. And it is biased form. And bias is 1. Represent 3.5 in this particular floating point representation. What is this bias? So bias is nothing. The exponent that I got here, right? It is represented in small e. What we do is we don't directly store this information in exponent. We add a number known as bias. Why we add? I will come to it. Don't worry, I will come to it. But just for now understand, I add a number known as bias with this exponent. Then that number gives me capital E. Okay, that is biased exponent. The binary representation of that I store here. So small e, I don't store it directly. Why? I will explain. So why I bias it? Basically, this capital E right here, we assume it to be a unsigned integer. If I assume it to be unsigned integer, I have to do few modifications. That modification is done through bias. That I will come to with example later on. For now, just understand, yes, we have to do a few modifications because this exponent will be always positive. This is also another important point. Exponent will always be positive. I mean capital E, not the small e. Capital E will always be positive. Okay. So two important points I have told you, that we don't store the base of the number system, and the capital E will always be a positive number. It can never be a negative number. Okay, it will always be positive. It is an unsigned integer. So now that you have got the information, pause the video and try to represent 3.5 in this particular floating point representation. Okay, so now I will start. So here 3.5 I should have mentioned, actually I will mention it here. 3.5 is supposed to be in decimal. Anyways, you can understand that it is decimal only, but we should mention, if nothing is mentioned, by default you assume decimal only. Okay, so I will mention it. This is base 10. Okay, this is based in. Now, first of all, I told you, right, I have to first normalize this. First thing is sign. So sign is positive only. So sign bit is 0. So the MSB will be 0, that I know. Of the 6-bit number, the MSB will be always 0. Okay, it is positive. Now I will normalize this. If I normalize this, this is 3.5. So which option is better? Which alternative is better? Shall I first convert into binary then normalize, or first normalize then convert it into binary? It's your preference. Okay, depending on the number you have to decide. So whenever integers are there, right, integers are always easier for me to convert to binary, right? So if integers are there, okay, the terms that are before the point, so I am seeing that I can easily write this 3 in a binary notation, that is 1 1. But what about the right hand side? Right hand side, it's a simple one, right? I know 0.1, this represents 0.5 in decimal. Okay, this fractional representation I have taught in the previous lecture, so I will not go through it here. Okay, but I know this is the representation, right? Or you can simply follow the rule that I have taught you. That also you can do. It will just take you more time. So this is the binary representation. Now I have to normalize it. How will I normalize? So this is 1 1. I have to move this point twice on the left. So this will be 0.111 on the left, multiplied by the base into what? I move this point twice on the left. So 2 places, right? So this will be 2 raised to power 2. Okay. I left shifted this. If I would have right shifted this, then this would have been negative. This exponent would have been negative. So like if I have a number that is 0.035 and I wanted to write it like 0.35, how would I have written it? It will be 10 raised to power minus 1. Just like that. Okay. So this is my mantissa, the fractional part. This is my small e. This is not capital E, right? So what is capital E? They have already told me that the bias is 1. So simply I will add 2 plus 1. That will give me capital E will be 3. So what is a binary representation of 3? Again 1 1, right? So but they have told me exponent has 2 bits. So it is exactly filling the gap. If let's say exponent came out to be only 1 in binary, then I would have added a 0 bit at the front. Okay, that's it. Because obviously adding any number of zeros doesn't make any difference in a number before point, right? So exponent is 1 1, capital E is 1 1, mantissa M is 111, right? And they have told me mantissa takes 3 bits only, so 3 bits are there. That's enough. So how will I represent the floating point number? So the floating point number will be like this. Floating point number, first sign bit will be 0. Then I will store the exponent. So this, right, this you have to remember actually. This is a standard and this you have to remember. So first comes the sign bit, then exponent, then mantissa. Okay. So exponent is 1 1. And mantissa is what? 111. Okay, mantissa is 111. So this is my 6-bit representation. 1, 2, 3, 4, 5, 6 of the particular number. What if I told you, what if I change this quotient now to 8-bit representation? Sign bit will always take 1. This got changed to 4 bits and this got changed to 3 bits. So this was for the 6-bit representation. If I change this to, like, if my exponent takes 3 bits, right? I have 1 1. So as explained previously, I have to write 3 in 3-bit format. So I'll just append a 0 at the front. That doesn't change anything, right? That doesn't change anything. So this will be 0 1 1. And my mantissa, I will change to what? Again 0 1 1. Okay. Not 0 1 1, sorry. 1 1 1 0. Just be careful here, right? If I tell you 0 1 1, then this actually doesn't represent this, right? What does 011 represent? 011 represents this 0.0111. So it is wrong. Appending 0 before point is on the leftmost side, right? And appending 0 after point, we should append at the end. So I will append at the end 0.1110. Anything changes? Are these two numbers same? Yes, nothing changes. So I will just choose this one. So my mantissa will be 1110. Okay, mantissa will be 1110. So now, just be careful. Here only students make the mistake. Okay, so in basics only you guys make the mistake. So my mantissa is 1110. Exponent is 011. So I can write sign bit will be 0, exponent will be 011, and mantissa will be 1110. Now what happens is this, right, isn't very pleasing to your eyes, to my eyes. Okay, it's this many numbers, we can mess up. So that's why we learned hexadecimal. Hexadecimal numbers are perfect for these type of conditions. Okay, so at the end what we do is we convert this into hexadecimal format to be more readable. That's the only reason. So what we do, we convert into hexadecimal. From binary we convert to hexadecimal for it to be more readable by you, by me, by the user. Computer only understands binary, but for us, we are very dumb, right? So we mess up things. So obviously we want to be it very readable. To make it readable, what I do is, generally in the questions they will tell you to convert this back into hexadecimal. So how do I convert into hexadecimal? I group in 4 bits. If I group in 4 bits, I will start from the right. Okay, so this is the 4 bit and this is the 4 bit. So this is 1110. So 1110 is what? It is 8 plus 4, 12 plus 2, 14. 14 is D. Not D, sorry, E. 14 is E. So this will be E. And this is 3 in hexadecimal. What about this? Now, if you have to represent in hexadecimal, you have to group from the left, right? So not from the left, sorry, from the right. So you will start from here. 4 bits you have grouped. These 2 bits are there, and I will append few extra zeros. So if I append few extra zeros, this will be 1. Okay, or I can use some other color. This will be 1. And this will be all ones. This will be F. Okay, in hexadecimal. So I hope you see what is the difference, right? How much just 2 bits can make a difference. So you have to be very, very careful about the representation. Okay, so now I will come to this normalization, how we are doing this implicit and explicit normalization. Okay, what is implicit and what is explicit normalization? These are standards that we follow. So what is implicit normalization? Just before that point, there should be a single one, always. It saves storage space but assumes leading bit is always 1. What do I mean by this? So if I have a number 101.01 and they're telling me apply implicit normalization, then what I have to follow? You have to follow only one thing. Just before the point, there should be only a single one. There should always be only a single one, always. Just before the point. That means, how will you convert? So the points you will move here, right? This point you will move here, so that just before the point I have a single one. That is the only condition that needs to be met. That's why it is written 1, XXX. 1 point, anything can happen. Okay, so this will be 1.0101. Now I move this point twice on the left, so obviously I have to multiply by 2 raised to power what? 2. I move this point 2 places. Another example, 0.001101. Okay, if I am telling you to apply implicit normalization, what does it mean? Just before the point there should be a 1. Okay, single one. It's not like I can do that 11.01. No, I cannot do it like this. Just before the one, there should be a single one. So it will be 1.01. 1, 0, 1. Into what? I move this point right thrice. I move this point right thrice. If I move this point right thrice, that means it will be negative because I'm moving right and I'm moving 3 digits. That's what it will be, -3. Okay. So that is the thing. And what is your mantissa here? Mantissa is the portion after the point. Mantissa is the portion after the point. After the point, whatever it is, the fractional part, that is the mantissa. Now you might say, sir, you told me you want to keep all the information about the number, but here you are only keeping this one. You are ignoring this information, this one. And you are correct. I am ignoring this information because it is implicit normalization. It is inbuilt in the normalization that the computer knows, you know, that there will be a 1. There will always be a 1. That's how we have normalized it. So by default, computer also knows when I will do the back calculation, when I will do the back conversion, it will add a 1 here before the point, right? It will add a 1 because we applied implicit normalization. I will tell to the computer that computer, I have applied implicit normalization. So whenever you will do the back conversion, you append the 1. So this also we don't store. We don't need to store because computer knows that Anish has applied implicit normalization. So computer will not store it. Okay, because we already know this 1 is there. It is implicit in the normalization. That's why the name implicit normalization. We don't need to store it. That's why we save a bit of space. Okay, so 1 bit space we save. That is the advantage of implicit normalization. Now you might have a doubt. If you have this doubt, very good. If you don't have this, so this will anyways come later on. That what if I have this number, right? 0.000. What do you have with this? Now can I apply the implicit normalization? The simple answer is no. You cannot apply the implicit normalization. And that is one of the drawback of this conventional floating point representation. Okay, that we will come to later on. We'll come to the drawbacks of this as well. Okay, so that's why we had to use a standard, that is IEEE 754. So after this, we developed from this to the IEEE 754. So we cannot represent 0 in this implicit normalization. That is a disadvantage. Okay, that is a disadvantage of this. So that is the case. And in explicit normalization as well, we cannot. So what does explicit normalization tells me? Explicit normalization tells me the number normalized till we get a 0. Till we get a 0 before the point, and just after the point we must have the bit 1. Just after the point we must have a bit 1. Okay, so what does it mean? So here, if I have a number like this, same number, right, 101.01, so I will go till 0, and just after the point I should have a 1. So how will I normalize? This will be normalized like this, 0.10101. How many bits did I shift? 3 bits, right? I shifted 3 bits. Previously for explicit I had to only shift for 2 bits. So this will be 2 raised to power 3. Okay. Here again the same example, right? If I have a number like this, if I have a number, okay, this was the number, right? Yeah, if I have an initial number like this, 0.001, 0.001101, how will I do the implicit normalization? I will shift the point here so that all the left bits are 0 and the right bits just after the point is a 1. Just after the point is a 1. So this will be 0. This will be 0.1101. Okay. So what is this? This is, I have shifted the point twice, right? I've shifted the point twice. So it is 2 raised to power -2. So that is the difference between implicit and explicit. Okay. Representing the same number in 2 different ways. Okay. So, like, this is the simple thing that I wanted to explain here. And for like this, whatever I am talking right now, I am explaining the conventional floating point representation. So in conventional floating point representation, if nothing is mentioned about normalization, you will choose explicit normalization by default. What did I say? In convention, this whatever we are learning right now is conventional floating point representation. We don't use this anymore. Okay. Anyways, they will tell you the type of normalization. If nothing is mentioned, then we will use explicit normalization for conventional floating point representation. So I'll write this point here. So for conventional floating point representation, we will choose explicit normalization unless anything is specified. If specified, obviously we'll choose that only, unless specified. Okay, so let's do an example, right? I think I have already done this. Assume 6-bit, okay, 3 bits explicit. Okay, we have anyways already done this, right? 3.5 floating point representation. I've already done this. So like we can only copy this only. Okay, they are telling me both with, okay, this time both with implicit and explicit normalization. Okay, so first I will do it with implicit normalization. So what I can do is, first I can convert this into binary. So binary I already know it is 1 1 1 in binary, but I want to do implicit. This is plus, right? This is plus, so obviously my sign bit is 0. Sign bit will be 0 plus. So I want to do implicit normalization. What does implicit normalization say me? Before the point there should be a single one, only a single one. So it will be 1.11. So I shifted the point only once left. So it will be multiplied by 2 raised to power 1. Okay. So from here I get my mantissa, I get my exponent. Bias they have given me as 1. So my capital E will be small e plus bias. That will be equals to 1 plus 3. Sorry, 1 plus 1, 2. 1 plus 1 is 2. And in binary, this is 1 0. Okay. In binary. So exponent is anyways 2 bits, so it is fine. Now, what is my mantissa is this, right? So my sign bit is 0. Then I will add my exponent. Exponent is 1 0. Then I will write my mantissa. Mantissa is 3 bits. Mantissa is 3 bits, but I have only got 2 bits. So what will I do? Tell me what will I do? I will append a 0 at the end, right? I can append a 0. It doesn't make any changes to the whole equation. So 110 into 2 raised to power 1. It doesn't make any changes. So this will be my 3-bit mantissa, because I cannot just leave that field blank, right? If they told me that mantissa is of 3 bits, so there is a space in the computer memory which has 3 bits, bit 0, bit 1, bit 2. So I cannot just leave that bit 0 blank. It doesn't work like that. Okay, so I have to store something, 0 or 1. So obviously I will store 0. It will not change the whole equation. So mantissa will be 110, not simply 11. Okay, mantissa will be 110. So this will be my 6-bit representation for a particular system, 6-bit system, floating point system. Okay, if I want to write in hex, I can write this in hex. So how will I write this in hex? Simply what you do is you convert it into 4 bits format, right? So this will be 0 1 1 0. So this is 4-bit, and then what am I left? 1 0 0 1 and another 2 zeros I can append, right? 2 zeros I can simply append. So this will be 1. This will be 4 plus 2, that is 6. So 1 6 in hex. Okay, 1 6 in hex, or this number in binary. This was for implicit normalization. Now for explicit normalization. For explicit normalization, what I will do? So I have to put the point here, right? Because after the point there should be a 1 always, and before it should be a 0. Okay, that is what was written here. Before we should get a 0 and after we should get a 1. Okay, like it is must, like it can happen that there are multiple ones after point. That can happen, that is fine. But after the exactly after the point, just after the point, there should be a 1. That is a condition, that is a must have. Okay, so this 11.1 in binary can be simply converted to 0.11, which we have been following right now, times 2 raised to power 2, because I have moved the point twice on the left hand side. So this time my exponent is 2 and mantissa is 111. So you can see how much a difference implicit and explicit normalization can make. Okay, so this is my M. My capital E will be small e plus bias, which is 2 plus bias is 1, so it is 3. In binary it is 1 1. So obviously now I can represent everything, which is sign is, it is plus, right? So obviously sign bit is anyways doesn't change, so sign bit is 0. Next part, right? Next part is the exponent part, which is 1 1. Next part is the capital E part. Capital E part. Capital E part is this, right? So basically, sorry, capital E part is done. Next part is the mantissa part, which is 111. So this is the 6-bit format. If I want to write in hex, how will I write in hex? I will group 4 bits. Okay. So this we have already done in the previous example. This is 1 and this is F. So in hex it will be 1F. Okay. In binary this will be 0 0. 0 1 1 1 1 1. Okay. That will be what it will be in binary. So few important points, whatever I have explained, that I have only told that the base of the system is not stored, because computer already knows that the base will be 2. That information is already given to the computer beforehand. Bits before the point we are not storing. If you understand that the bits before the point we are not storing, why? Because I have already all the information bits after the point. I already have all the information bits after the point. Why floating point representation? Because the point, right, is always floating. Okay, I can shift around the point and the exponent will vary, but still I will not lose any information about the particular number. Okay, and exponent will always be an integer. Exponent can never be a fraction. I think few of you can have this doubt that what if the exponent is a fraction? How will I store it? Exponent will never be a fraction. Okay, so why will exponent never be a fraction? Because I can move this point in a whole number. I can move this once at the right, twice, thrice, 4 times, 5 times. I cannot move this point half a times on the right. Can I ever do it? No. I cannot move this point just between this 0. Can I do it? No. Okay. So I will just say, why will exponent never be a fraction? Because I cannot move this point between this 0, right? You will say, sir, I move this point between this 0. I will break this 0 down and move this point here. Keep this point here. आधा 0 उधर, आधा 0 इधर. Okay? आधा तू खा ले, आधा मैं खा लूंगा. ऐसा करोगे तो गेट में भी नंबर आधे आधे आएंगे. ठीक है, पूरा नंबर नहीं आएगा. तो we cannot do it. We cannot do it. So obviously, this key point you have to keep into your mind, that exponent will always be an integer. It can never be a fraction. And your capital E will always be greater than 0. Why? The bias makes sure that your capital E will be always greater than 0. Okay, these few points you have to keep in mind. Now let's come to that only. Let's come to the biased exponent. So if I have 4 bits for the exponent, then can you tell me what will be the signed range? If you have studied number systems, then you will be able to comment. If you haven't studied number systems, I will just break you down with a small example. Okay, so if I have, let's say, if I have 2 bits, how many numbers can I represent with 2 bits? 0 0 0 1 1 0 1. Now you might say, sir, I want to represent sign numbers as well, negative and positive numbers. So how many numbers in total I can represent? So range will always be 4. That is 2 raised to power 2. That is the range. But I want to represent sign numbers. So what scientists did was they moved this bias, right? They told that this 0 0 actually represents minus 2. This 0 1 represents minus 1. Computer knows it. Okay. This 1 0 represents 0. This 1 1 represents 1. I know this is not exactly the conversion from binary to decimal, but it is coded. Okay. Something like, just for now, just take the example, it is coded. Okay. So if I want to represent sign numbers, I cannot represent from your 0 to 2 raised to power 2 minus 1. If I had only unsigned, like if I had only unsigned numbers, right, then this 0 0 would have been 0, 0 1 would have been 1, 1 0 would have been 2, and 1 1 would have been 3. So I would have been able to represent from 0 to 3. But now I am only able to represent from 0, like that's why this 2 raised to 2 square minus 1, that is 0 to 3. I can only represent from 0 to 1. But obviously range has not reduced, right? I can also represent negative numbers. So what we are doing is basically we're representing the same range is same numbers only, but I am representing extra negative numbers. So if I have a 2-bit number, then the range, right, which I can represent the negative and positive numbers is will start from minus 2 raised to power 2 minus 1 2 plus 2 raised to power 2 minus 1 minus 1. How did this 2 minus 1 came? The range got half, right? Because 1 half is for positive numbers, 1 half is for negative. Previously I had only sign numbers, so everything was positive. But I had to now assign an half for the negative numbers. So that's why this 2 minus 1, like it's basically 1 by 2, right? 1 by 2 is 2 raised to power minus 1. That is what is happening over here. So this is just a basic overview. If you want to learn more about this range and all those things, you can study the digital electronics full course. This is like this, we don't need to go much in depth here. Okay, so basic thing I talked about. So if I have n bit, right, then what will be the range of a n bit signed number? So it will start from minus 2 raised to power n minus 1 to plus 2 raised to power n minus 1 minus 1. Okay, this extra 1 is for the 0 basically. So if I have 4-bit number, then I can represent minus 2 raised to power 4 minus 1, that is minus 8 minus 2 cube 2 plus 2 raised to power n minus 1, that is 3 minus 1 2 into cube, so 2 cube 8 minus 1, that is 7. Okay, the eraser is too big. So I can represent from minus 8 to plus 7. I can represent from minus 8 to plus 7. But I told you, right, we store the exponent as an unsigned integer. So what the scientists did was just convert it back into unsigned. How do I convert it back into unsigned? I will just simply add the number that will make the lowest number positive. How much do I need to add here? 8. How much do I need to add? 8. So if I add 8, so now I was representing from minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, and so on. Okay, and so on to 7. So what I'll do, I'll just add 8 with the lowest number. So this will be 0, this will be 8, this will be 1 plus 8, this will be 2 plus 8, this will be 3, and it will go on here. Maximum number, like for this is just the unsigned range, right? It is just the unsigned range. That will be, it will be 15. Okay, so what is this? This is just the unsigned range, right? From 0 to 2 raised to power n bits minus 1. just the unsigned. That's what we did. Okay. So this is what we do. So that's how the bias came. The bias is this number. This number is the bias basically. To make it unsigned, we add this number to make it positive. Now, one more thing. Can I predict this bias? If the exponent is of 4 bits, can the bias be fixed? The answer is yes. The bias will be fixed. How? If I have 4-bit number, right? I know the minimum number for that 4-bit number, signed minimum number for that 4-bit number will be -8. What is this actually? It is 2 raised to power n minus 1, right? And I have to add this number, and that will make this minimum number 0 if I add this same number. So this is basically the bias. This is the bias. So if I have a k bit number, let's say k bit number, right, for the exponent, k bit exponent, k bit exponent, then can you tell me what will be the bias of that? The bias will be 2 raised to power k minus 1. I use the same thing, right? I just need to add this, like this is a negative. If I add the same number in positive, it will be 0. Plus k minus k is 0. Not k, let's take plus x minus x. Plus x minus x is 0. I need to add the same number, right? To make it 0. I want to make the lowest number 0. So the bias is this. One more thing is that, what is my exponent? Capital E. Capital E is small e plus the bias, correct? Now in our example, our bias is 8. Bias is 8, right? So it is e plus 8. We are adding 8 to all the exponents, right? Whatever numbers we have, we are adding it. This is also called as a particular code that is known as excess 8 code. So don't get scared by this name excess. Excess 8 is nothing. We are just adding all the numbers by 8. That is the meaning of this excess 8. If my bias was 16, then what this name would have been? This name would have been excess 16. If the bias is 16, can you tell me how many bits will be my exponent? If the bias is 16, how many bits will be my exponent? This is 16. 2 raised to power k minus 1 is exponent. So 16 is 2 raised to power 4. So 4 equals to k minus 1. So k is equals to 5. So if bias is 16, then my number of bits for the exponent will be 5. So you can go backwards from bias to the number of bits of exponent, or you can go from number of bits from the exponent to bias. One thing will be given and you have to find out the other. Okay, so like this they can play with you. So this is one thing about the bias and excess 8. So like here, like I just given you example. If my original exponent, that is e, small e, was -8, then I bias it with the excess 8 code, capital E, it will get biased to 0. I just simply add 8, right? 1, then it goes on till 15. Okay, nothing much to explain. That's the only thing that you have to keep in mind. This is the important portion. If the exponent is k bit, I will write this better. Then our bias will be 2 raised to power k minus 1. That's it. That is the only thing that you need to keep in mind. This is the important thing that we have to take away. And this excess 8 code, right? This also you can highlight. Okay, so that is about the biased exponent. So one more thing, if the number is represented in implicit mode, in implicit normalization, then what will be the formula? What will be the value formula? Basically, this thing is constant for both of them, right? -1 raised to power s, -1 raised to power s. this is just taking into consideration the sign of the number. Now if it is implicit, for implicit it is implied, we already know that the value just before the point will always be 1. There will always be a single 1. So I will write this one. This is implied in the implicit normalization. Whatever after the point, that is the mantissa. The fractional part is the mantissa, m. And I have to get back to my original value. So this should be multiplied by 2 raised to power my original e. But in the representation, we don't store original e, we store exponent. So we change this through capital E minus bias. How did this came? So my e was equals to e plus bias, right? We just biased it. So my small e will be what? Small e will be capital E minus bias. Okay, simple conversion. And here in explicit, I told you the value before the point is a 0, and after it is the whole mantissa. After it is a whole mantissa. So we store the whole mantissa after it. Okay, m into the same thing only. This thing is same only. Whatever exponent will come, that will come according to this explicit normalization. So it will also be e minus bias, and that like this initial exponent was also according to the explicit normalization. So now I hope you are able to understand what is floating point representation, right? I know you got scared by seeing this formula. Okay, so that's why I told you don't have to stress about this. Let me just explain. You will understand everything. So now I think you have got a bit of confidence that you will be able to write, if a floating point representation is given, you will be able to convert it back. So now you will be able to understand this formula. And if you are enjoying, so make sure you hit the like to the video. Okay, and comment below how you are feeling. If this concept is like if you are feeling that this concept is totally crystal clear on your mind. If this concept is totally crystal clear on your mind, then solve this question. Okay, so a 16-bit register is used to store floating point numbers. The mantissa is a normalized signed fractional number, and the exponent is represented in excess 16 format. Determine the 16-bit representation of plus 45.75 in decimal in this register. So the register has 16 bits. Okay, register has 16 bits. So if the register has 16 bits and they have not told me anything, they have not told me how many bits does the mantissa take, how many bits does the exponent take. The number of bits taken by the sign is 1. That is already known. So S takes 1 bit. So 15 bits are left, right? So my representation will be somewhere like this. This if I copy and paste here. So in this, 1 bit is gone, but this whole register is of 16 bit. Okay, how do I find out the number of bits of exponent and mantissa? They haven't told me, but they have given you a small information. The exponent is represented in excess 16 format. If the exponent is represented in excess 16 format, that means what is the bias? Bias is 16. And how can I write the bias? Bias can be written as 2 raised to power k minus 1, where k is the number of bits of the exponent format. So from here, I will be able to find out my exponent. K will be 5. Okay. So this is 5 bits. So now it became easy, right? Overall, this is 16 bits. 1 bit is for sign. 5 bits is for exponent. So remaining bit, 10 bits will be for mantissa. 10 bits. Now I got all the values. Now I just need to convert. So how can we convert? So this is plus 45.5. So it is plus. So obviously the sign bit will be 0. Sign bit will be 0. So sign bit is 0. Now I need to convert the original number 45.75. Now you can convert it in two parts, the fractional and the original. So you can solve that using that basic method that I told you in the previous lecture, or you can use a weighted binary, right? So 45, the maximum 2 raised to power number that I can represent 45 is 32. How much is remaining? 13. Then it can be 8 plus 4 plus 1, right? It can be 8 plus 4 plus 1. 8 plus 4 plus 1. Okay. So this is what? This is 2 raised to power 5, 2 cube, 2 square, 2 raised to power 0. So this is the sixth position. This is the sixth position bit. Okay, and this is the zeroth position bit. No, six. Sorry, this is the fifth position bit. And this is the zeroth position bit. So 0 bit will be 1. This will be 0. Then I will be 1. Then I will be 1. This is third. So 4 is 0. Then again I have a 1. What about the fractional part? Fractional part is pretty simple. I can directly see that this is basically 0.5 plus 0.25. So this is 2 raised to power minus 1 plus 2 raised to power minus 2. So again the same thing only. So here this comes, the bit just after the point should be set, that is 1. The bit one place after the point should also be set. So the binary representation of this number will be this. First thing is you have to do this. Now we have done this. Okay. So now you have to normalize. Okay, actually previously if I told that you can normalize it first, then you can change. Yeah, that also can be done. You can normalize it here, then also you can convert, but that will be lengthy. That will be very, very lengthy. Okay, that also can be done. There is no issue with that. But like you have to follow the rules, right? Now nothing is mentioned. Nothing is mentioned. So as nothing is mentioned, assume explicit normalization. Assume explicit normalization. Okay. So if I assume explicit normalization, so everything should be after the point. Okay, and there should be one, right? So it will be like, if I do the explicit normalization, it will be 0.10110111. So how many places did I moved it? So this was 1 2 3 4 5 6 bits, right? I have 1 2 3 1 2 3 6 bits I moved. So this will be on the left I moved, so this will be 2 raised to power 6. Okay. Now how many bits is my mantissa? So this is actually my mantissa, but how many bits they have provided for the mantissa? They have provided me 10 bits. They have provided me 10 bits for the mantissa. How many bits are these? 1 2 3 4 5 6 7 8 8 bits, right? I have only got 8 bits, so I will need to add extra zeros on the right hand side. So this can be converted 0.1011 0.11110. Okay, 101 101 110 and 0. Now it is my mantissa. What about the exponent? So this is the small e. I have to bias it. So what will be my biased exponent? Bias exponent will be this small e plus the bias, and they have told me that they are using excess 16 code to represent the exponent. So it will be 6 plus 16 22. This is in decimal. Again I have to convert this into binary. Everything will be in binary inside computer, right? So again I can write like this: 16 plus 4 plus 2. So this is 2 raised to power 4 plus 2 square plus 2 raised to power 1. Okay. So here my 0th bit is 0, first bit is 1, then second bit is 1, then it is 0, then it is 1. Okay, it is 1 0 1 1 0. Now how many bits I have for exponent? 5 bits, and this is 5 bits only, so I don't need to modify this. Okay, this is my exponent. So now I will finally write my floating point representation. Okay, so the first bit is sign bit, so it will be 0 as it is a positive number. Next I will write the exponent. Exponent is 1 0 1 1 0 1 0 1 1 0 1 0 1 1 0. Okay, next is what? Next is my mantissa. Next is my mantissa. So mantissa is what? Mantissa is this, right? 1 0 1 1 0 1 1 0 1 1 0 1 1 0 1 1 0 1 1 0 1 1 1 0 0 1 1 0 0. Okay, so let me just note it down. 1 2 3 4 5 6 7 8 9 10. Yeah, correct. So this is my whole floating point representation. Now if they ask for the hexadecimal, so you will group everything in 4 bits, right? So that's easier for you to write. So this is a mess, right? 16-bit, this is a mess. So obviously we don't like to represent it like this, so we divide it into 4. We divide it into hexadecimal, right? Group of 4 bits. So 1 1 0, then this is 1 1 0 1, then this is 0 1 0 1 0, and this is 0 1 0 1 0 1 0 1. This is 4 plus 1, so this is 5. Okay, next this is 1 0 1 0. It is 8 plus 2 10, that is A. 1 0 1 0 1, so it is 1 0, sorry, yeah, 1 1 0 1. So 1 1 0 1 is simply 8 plus 4, that is 12, plus 1, that is 13. 13 will be D. Okay, 13 will be D, and it is 1 1 0 0, that is 12 is C. So you can write it like this. Sometimes they write like this, okay, or they can write it like this as well. H also represent for hexadecimal, or in programming language, if you have done C programming, you know you can represent hexadecimal numbers in code like this. Also 0x represent hexadecimal, 5A DC. Okay, so like this is the answer. That's it. This is the answer of this particular thing. Now this portion is finished. So yeah, so that is like what is written. Why floating point representation is needed, I have explained, right? Why it is needed, because we had to represent much wider range of numbers. So here we'll understand how can I represent much wider range of numbers. So they have asked us that find the range in the previous example if exponent is represented in XS32 format instead of XS16 format, then what will be the range? Okay, what can be the range? Now also determine the positive minimum and negative maximum possible values that can be represented. So this also will determine. So first let me determine the maximum, let me determine the range. For me to determine the range, right, I have to determine the minimum value, positive minimum value, or like sorry, for me to determine the range, right, I just have to determine the maximum value. Why? I will explain. So what is the maximum value? Maximum value I have, like for the previous example, I had a 16-bit register. So first bit was the sign bit. Okay. Next 5 bits were the exponent bits. And the next 10 bits were the mantissa bits, correct? What can be the maximum value? What can be the maximum value? Everything 1 except the sign bit, because sign is just it just tells us a sign. Except the sign bit, if everything is 1, that can be the maximum value. So all the mantissa bits are 1, all the exponent bits are 1, sign bit is 0. 0 represents a positive number. So what is this actually? This represents what? So this currently is a 5-bit number, right? And exponents E is all ones. It is 5 ones, correct? 1 2 3 4 5, 5 ones. In decimal, what is it? In decimal, it is simply 63, correct? 5 ones is simply 63. Yes, 5 ones is 63. Now they are telling me that we are representing this in the XS32 format. So what will be the actual exponent? Capital E was equals to E plus bias. That is what my capital E was. So my small e will be E minus bias. Bias, if I am representing in XS32, what will be the bias? Bias will be this 32, right? So 63 minus 32, that is 31. Okay, that is 31. So exponent is 31. Okay, we got it. What about mantissa? I have 10 of these ones, right? So if I write this properly, this will be like, I am using, assume, like in the previous question they have told me that they are using, like nothing is mentioned, so I am using explicit normalization. So if I back calculate it, it will be, if I am using explicit normalization, just before the point there will be 0, just after the point there should be 1, which is there. So everything is 1. So 1 2 3 4 5 6 7 8 9 10. Okay, this is my number, right? And my sign bit is what? Minus 1 raised to power my sign bit is 0 into 2 base raised to power the exponent. Exponent is 63 minus 32. So what is this actually? So I don't like working with points. I hate working with points. So I will move this point here, right? So it is 2 raised to power 31. So I will move this 10 places. I'll move this 10 places. Okay. So if I move this 10 places, what will happen? This minus 1 raised to power 0 is 1 only. Okay. So I will write like this. It will be 1 1 1 1. Just hold on. 1 1 1 1 and 1 1. Okay. These are my 10 bits. This is in binary multiplied by 2 raised to power. This is 31. So I right shifted the point by 10 bits. So this will be 21. Okay. Now, if I observe, this is actually equals to what? This can be written in a very beautiful format. What is that? How many bits I have? 10 bits. Let's take this example, right? If I have 2 ones, how can I write it? This you can either write like this, that it is 2 raised to power 1 plus 2 raised to power 0, or it can be elegantly written like this as well. This is what? This is just before 100, just before 100. So if I subtract 1 from 100, I will get back this value. What is 100? 100 is 2 raised to power 3, and I have to subtract 1 from this, I will get back to this value. Correct? So if I have 2 bits, that means here this will be 2 plus 1 minus 1. This value can be represented as 2 raised to power the number of bits plus 1 minus 1. So exactly that is what I will do. So this can be written, this has 10 bits, so it will be 2 raised to power 11 minus 1, okay, into 2 raised to power 21. Now this one is like almost ignorable, right? This one is negligible. This one is almost negligible. Still I can write this, I don't care about this. So this will be actually equals to what? This one is negligible. I can ignore this because if I subtract 1 from 2 raised to power 11, this one is negligible. So it will be almost equals to 2 raised to power 11 into 2 raised to power 21. So it will be almost equals to 2 raised to power 32. This is the maximum value. That is what we are calculating, right? This is the maximum value. What is the minimum? What is the minimum? Just add a negative sign. Just add a negative sign and you will get your minimum value. So just I will change my sign bit to 1. That will change it to negative. That will change it to the maximum minimum value that can be represented, right? So that is the minimum value only. Okay. So the lowest value. So minimum value will be, this is the maximum. Min is minus 2 raised to power 32. What is the range? Range is maximum minus minimum. So it is 2 raised to power 32 minus of minus 2 raised to power 32. So it is 2 times 2 raised to power 32. It is 2 raised to power 33. Now let's take the same example with fixed point representation. Fixed point representation. Fixed presentation. So if I had a fixed point representation, right, what is the range? I have 16 bits. If I had 4 bits, what was the range? Previously I discussed, right? If I had 4 bits for fixed point representation, what was the range? It was 2 raised to power 4 minus 1 minus 2 raised to power 4 minus 1 minus 1, correct? It was from minus 8 to 7. Okay. So overall range was simply 15. Not 15, sorry. Overall range was 16. Why? Because a 0 is also included, right? 0 is also included. So 16, I can represent total 16 different values. I can only represent total 16 different values. What is that? That is simply 2 raised to power 4. That is how much I can represent. So if I have 16 bits now, how many different values can I represent? If it is a fixed point representation, it will be 2 raised to power 16. What will be the range? Range, just hold on. Range will simply be this 2 raised to power 16 only. What is the minimum value? Minimum value is 2 raised to power 15 minus 2 raised to power 15 to 2 raised to power 15 minus 1. That is the range. And what is the range here? Overall range is 2 raised to power 33. That is humongous. Humongous. Okay. Can you see the difference? Can you see the difference? How much it is differing? Okay. And what is the number range? This is the number of different values that I can represent here. Okay. What is the number range? Number range is from minus 2 raised to power 32 to plus 2 raised to power 32. Although I ignored a 1. Okay. Just approximately I am calculating this. Okay. So can you observe? I can represent so much bigger number here than this with same number of bits, with 16 bits. And I can represent very small number here as well. Okay, very small number here as well, because it is a floating point. So point can come at the start. Okay. So I can represent so many numbers in floating point representation than fixed point representation. So that's why we use fixed point representation. Now, of course, this has few problems. What is the first problem? The first problem is, what if everything is 0? What if? So next question they are asking. So this is the part 1 that has been finished. Also determine the positive minimum and negative maximum possible values. So you say positive minimum 0, sir. We can represent 0. But I told you at the starting, we cannot represent zeros. We cannot represent zeros here. So we have to understand what is the minimum value that I can represent. Why we cannot represent 0? The first rule was that when I am applying implicit normalization or explicit normalization, I told you in implicit normalization, the number just before the point must be a1. There should be a single one just before the point, and the number after point must be a1 for explicit normalization, and the before it should be 0. So there is I can never normalize this value. Can I ever normalize this value? No. If I follow these two rules, this number doesn't lie. Okay. So I cannot represent this. Cannot represent 0 using our normalization rules. Cannot represent 0. Okay. So here I have the sign bit, the exponent bit, the mantissa. So if I tell you that if everything is 0, right, you will say, sir, then it will be 0. No, it will not be a 0. Okay. In conventional floating point representation, this is not a valid representation. Why? Because we can never get this value, right? With our rules, with implicit and explicit, I can never get all zeros. So minimum will not be 0 and I cannot represent 0. So what will be the minimum value? How can I represent the minimum value? In both implicit and explicit, just before the point and after the point, there must be a 1. There must be a 1. So the minimum value of mantissa, like a 1 should be present no matter what. If I am using explicit normalization, 1 should be here. Okay. So it can be 1 0 0 0 0 0 0. Like if I am representing in 16 bits, 4 4 then 2. This is for explicit. If I am using implicit, my mantissa can be all zeros. 0 0 0 0 0 0. Yeah, if I told you it is not a valid representation, for explicit it is not a valid representation. I should have discussed this is not a valid representation for explicit. In implicit, all zeros means what? Basically it is 1.0. So all 0 here, 0 0 0 and 0 0. This means what? If mantissa is this, that means computer already knows, right? It will always append a 1 before the point if it is implicit normalization. So what computer is smart. So what it will do is it will append a 1, 1.0 0 0 0 0 0 0 and 0, whatever how many zeros are there. Okay. So I can never represent my zeros, okay, in implicit or explicit. But now I will solve according to explicit normalization. The minimum positive value will change for implicit and explicit normalization. I will talk about that. Okay. But first I will solve with explicit normalization because the question I solved was with explicit normalization. Nothing is mentioned. So by default I will choose explicit normalization for conventional floating point representation. So if I choose explicit normalization, my minimum mantissa value can be this, because just after the point there has to be a 1. There must be a 1. If I choose here once, that is fine. But if these are ones, right, that will just increase the mantissa value. And now I want to choose the minimum possible value. So this is all ones. Great. So this can be written as 0.1. And I will choose the minimum possible exponent. What is the value of minimum possible exponent? All zeros. Can all zeros is allowed? Yes. If I ever tell you the range of capital E, right? Here, the range of capital E starts from 0. That is the minimum possible value. So original exponent will be just the most lowest value. So because I have to choose the minimum possible value, so that's why I am choosing the lowest values. So capital E can be all zeros, and if capital E is all 0, that means my small e will be E minus bias. My small e will just be minus of bias. Okay, so this will be minus of bias. What is bias? Bias in our case is excess. We are using excess 32, right? So in our case it is 32. Okay, so capital E is 32. So the smallest positive number, this I can come back, right? Sign is 0, positive number, so the sign V2 will be 0. So minus 1 raised to power 0 into exponent into, first I will write the mantissa. Mantissa is this, okay, which is, it is explicit normalization. So after point a1 will come and everything else is 0 times base raised to power the exponent, that is minus 32. So this is the minimum number that I can represent. So this, if I simplify it, this is 0.1 into 2 raised to power minus 32. This is for explicit. And what about the second part of this? Negative maximum. Negative maximum meaning the number that is closer to 0. Maximum, it is talking about maximum, right? And more negative is a lower value, like minus 5 is a lower value than minus 4. Correct? Minus 5 is a lower value than minus 4. So which one is the maximum out of this? Minus 4, right? It is the higher value. Okay, so they are telling me maximum negative value. So the more closer I am towards 0, so I need to go more closer towards 0. It will be what? It will be just the negative sign of this. So this is the lowest positive value. Okay, lowest positive value, and the highest negative value will just be the opposite sign of this. Okay, the sign bit will be 1, everything else will be same, just the sign bit will be 1, right? So S will be 1. If S is 1, that means minus 1 raised to power 1, everything else remains as it is. Okay, I will just simply do the copy paste. Okay, so this will be negative. So can you observe how much low value I can, like how much precise I am? But this is not 0, right? I cannot represent 0. That is the only issue. So maximum negative that I can represent is this, but I cannot exactly represent 0. This is the closest that I can get to 0 from the negative side. From the negative, this is my number line. This is 0. Okay. From the positive side, if I approach the maximum positive that I can approach from that I can approach from the positive side is 0.1 2 raised to power minus 32. Then the computer says I am surrendering. I cannot represent any lower value than this. And if I come from the negative side, not the maximum, the minimum lowest number that I can represent is 0.1. Minimum lowest positive number that I can represent is 0.1 into 2 raised to power minus 32. The maximum highest negative number that I can represent is minus 1 into 2 raised to power minus 32. What does it mean? If I come from the negative side, I can only reach this far. I cannot go exactly 0. The computer will surrender, say I can only represent this much. I cannot go exactly towards 0. Okay. So that is the problem with this. So there is a solution that we'll discuss. Okay. So if let's say if all this was for explicit, now let's solve the same thing for implicit. For implicit, mantissa being all zeros is actually allowed. Mantissa being all zeros is actually allowed. Okay. Sign. This is my exponent. Okay, I will not write here. Signed, exponent, and mantissa. So Mantis all zeros is allowed in explicit. In implicit, it is not allowed. Sorry. Mantissa being all zero is allowed in implicit. In explicit, it is not allowed. So here all zeros can be there. Exponent can also be all zeros. And sign for the minimum positive number, it will be 0. For the maximum positive number, it will be 1. Sorry, for the maximum negative number, it will be 1. This is for the minimum positive number, and this is for the maximum positive number. Okay, so now let's do it for the implicit case. For the implicit case, I already know that it is a 1. Okay, I already know that it is a 1. So Mantissa will be 1 comma m, right? Mantissa is 1 comma n. If you remember from the derived formula, Mantissa was 1 comma n. So it will be 1 comma 0 0 0 for however many zeros I have. This is minus 1 raised to power 0 into 2 raised to power the exponent minus the bias. Bias is 32, exponent is 0. So it will be 2 raised to power 0 minus 32. Okay, so this will be equals to basically 2 raised to power minus 32. This will be the minimum value that I can represent. Here, if I want to write this in a better manner, this will be minus 2 raised to power minus 33, and this will be 2 raised to power minus 33. Okay, so obviously this has better precision than implicit. Like, you lose out on precision because you are saving a storage, right? You are not including this one, you are not storing this one, so you are saving, but you are losing out on precision. So there is a factor. Obviously there is a trade-off. Now for the negative, everything will be same. It will be minus 1 raised to power 1 only, 1.000 until 0 into 2 raised to power 0 minus 32. Everything will be same here. So this will be minus 1 minus 2 raised to power minus 32. Okay, so like this is the minimum value in implicit. So I solve for explicit, implicit, the maximum negative number, the minimum positive number, the maximum positive number, the minimum positive number. 4 things have been solved. So that is the problem, right? Here we can see I have found out the maximum positive number, that is also known as the real max, the minimum positive number, that is known as the real min, the maximum negative number, that is the real minimum. Okay, real minimum meaning which is nearest to the 0 from the negative side, and the maximum the minimum negative number, that is the real max. So don't get confused with the names, please don't get confused, just concept you need to understand. I hope you got the concept that this is called as minus of real max, negative of real max. Okay, so this is actually my usable range. If I go below my real min, I have a problem. If I go above my real min, I have a problem known as, if I go above my real max, I have a problem that is known as overflow. If I go below my real min, it is known as underflow. And the name is intuitive, so I don't need to explain much things here. Okay, so obviously this is my usable range, which is a very, very good thing, which is a very, very good range, but I am missing out, right? That is the problem. This overflow will always be there anyways. For normal fixed point representation, overflow is anyways there, but underflow, there is an underflow problem here. Okay, and if you know a bit about overflow, like I will not go too much in depth here, but basic thing, you know that if I have if this is the real max, and if I add 1 with this, right, what computer does is it has a circular loop. So it will just come back to the negative of real max. So again, it will follow this whole circle. If you know a bit of concept about overflow, you'll understand this thing. If you don't know, ignore. Totally ignore this. Okay. Overflow has been taught in digital electronics number system. Okay. So here, like, the same thing is written that if it occurs when a number exceeds the maximum representation value. Okay. Representable value. If I exceed than that, obviously, we cannot represent that. Underflow is the if we go below our minimum representable value. Okay. These are things. And normalized representation, obviously I have discussed about this, that how the mantissa is represented, right, as implicit or explicit. Okay. However, this means zero and subnormal. What is subnormal? That is very small values that are below this real min, right? Underflow, we cannot represent. If I am using normalized representation, I cannot represent very small values and zero. That is a problem. And zero is a very, very important number, right? Because obviously Indian invented zero, so we had to include zero. And I'm just joking, because zero is an important number. How can you not store zero? Zero is a very, very important number, right? So we have to store it. For that, a convention came that scientist made, that is IEEE 75, that we'll learn. So here we like the floating point representation allows to span a wide range of values, balancing both precision and storage efficiency. I think you can see with 16 bits how big of a number I can store. But with fixed point representation, that was not totally possible. That was totally not possible. However, the design of representation impacts both range and precision. What does it mean? So obviously, engineers have to be smart, because when you will go to work in the industry or somewhere, right, you have to make very smart decisions. This is also a very smart decision. So how many bits you will provide for the exponent field and how many bits you will provide for the mantissa field, that decides the range and the precision of your representation, floating point representation. If you observe, if I give more bits to the exponent field, what will be possible? Basically, this exponent will be higher. If this exponent is very high, right, I can show very high values. Like, I can store very high values. Okay. I can store very high values and very small values. I can store very high values and small values, because this exponent ultimately decides the positive and negative. Ultimately decides the 2 raised to the power 32 is the very high value and 2 raised to the power minus 32 is the very small value. So this exponent decides the overflow and the underflow. Mantissa doesn't decide. Mantissa doesn't have the control over the overflow or underflow. So mantissa doesn't have control over overflow and underflow. So if you want to have very high range, then you will choose the exponent bit field to be higher. Okay. Now, precision is determined by the size of the mantissa field. A larger M provides better precision, as it allows more bits to represent the fractional part. Okay. If I have only 2 bits, let's take 2 bits to represent the fractional part, and in the other example, if I have 4 bits to represent the fractional part. Okay, this is 0.100, this is 0.1000. Okay, so in this case, the exponent is 4 bits. So let me take an example. Okay, let me take an example here. So let me take an example, right? So if I have a 6-bit, okay, not 6-bit, let's take example of 7 bits only. So 1 is gone for sign, 2-bit is mantissa, and 4-bit is exponent. Okay, here same 7-bit register, 2-bit for exponent, 4-bit for mantissa. I want to represent this number, right? 1.01. Okay, I want to represent this number. So here what happens is, if I represent in this first format, right, first and second format. In the first format, the mantissa has 2 bits. If the mantissa has 2 bits, then what will happen? I will use explicit normalization. If I use explicit normalization, what I will do? I will do 0.101, okay, into 2 raised to power 2 raised to power so this will go here 1 point, yeah, 2 raised to power 1 only, okay, into 2 raised to power 1. Okay, so what will be the problem? My mantissa has only 2 bits, but this is 3 bits, so obviously I have to ignore a bit. Which bit I will ignore? I will ignore this bit, right? Because the rightmost bit has the lowest weightage. This is what? This is 2 raised to power minus 3. This is 2 raised to power minus 1. So rightmost bit has the lowest weightage. So I will ignore that bit. I will ignore that bit. Because I have only 2 bits space, right? I cannot like get bit from the heaven. Okay, I cannot make bit at that point of time. So obviously I have to ignore this. This will be ignored. So my mantissa will be 0.10. Okay, into 2 raised to power 1. So what will be stored in the computer? In the computer, exponent will be what? Exponent will be e plus bias. So if it's a 4-bit exponent, then what will be the bias? Bias will be k minus 1. So it will be 8. So this will be 1 plus 8, that is 9. And how do we represent 9? So 9 is represented 1001. Okay, so sign bit will be 0. Then I will have 1001. Then I will have the mantissa. Mantissa is what? 10. Mantissa is this, right? Mantissa is this 2 bits only, because I have only 2 bit space. Now let me come to here. So if I come here, the same number, right? Again I will apply explicit normalization. So this will be 0.1010 I can add, because I have 4 bits now for the mantissa. 4 bits for the mantissa. So this is my mantissa. What is my exponent? Exponent is of 2 bits. So bias will be 2 raised to power 2 minus 1, that is 1. Sorry, 2 raised to power 1, that is 2. So bias will be 2. So this, right, is equals to what? 2 raised to power 1 again. So it will be e plus bias, which is 1 plus 2, which is 3, which is 1 1. So here sign is 0 only, exponent is 1 1, and I have 4 bits for the mantissa, which is 1010. Which one is more precise? Which one is more precise? This one is more precise. Why this one is more precise? Now I will come to my original number system, decimal. This is stored in computer, these 2 things are stored in computer. Now the user wants to fetch the result. User wants to see which one, what is the number actually, what is x equals to. This is equals to x. What is x? So computer will do the reverse calculation. So here if the computer does the reverse calculation, how it will do the reverse calculation? So here, this is my exponent, capital E equals to 1001, which is equals to 9, which is equals to E plus bias. So my E is equals to 1, because bias is 8. And this is my mantissa. And this is explicit normalization. So I know a 0 will come, and this will be my mantissa, and this will be 2 raised to power my exponent, that is 1, which is equals to 1.0, which is equals to 1, which is equals to 1. Okay, here, so this is my number. This was my initial number. Computer tells me, user Anish, this was your initial number that you gave me. Okay, and here what will be my initial number? So if I calculate the exponent E is 3, which is equals to E plus bias. Bias is 2, so E will be simply equals to 1. So this is my mantissa, again explicit normalization, into 2 raised to power 1. So that is equal to 1.01. Now system 1 is telling me that 1 was the initial number that you gave me, Anish, and system 2 is telling me 1.01 is the initial number that you gave me. Which one will you pick? Which one will you choose? So you will choose obviously the second one, because this was not the initial number that I gave. I gave 1.01. What happened? I told you, right? This information got lost. Because I didn't have enough mantissa bits to store the information. That's why the statement that the larger M provides better precision as it allows more bits to represent the fractional part. I have more bits to represent the fractional part. So obviously there is a trade-off. Here, what is the maximum value that can be represented? Maximum value will be simply this exponent maximum value, right? Which is all ones, which is 2 raised to power exponent all ones minus bias. So 8 minus this all ones, right? If 4 ones are 15 minus 8, 2 raised to power 7. Okay, 2 raised to power 7 here. And here the overflow or the real max will be very, very lower. This is just, I have 2 bits, so I can only represent 2 raised to power 1. That is the maximum that I can represent. So you can see, you have to make a trade-off. There is a balance. So you have to balance everything out. So like, don't worry, you don't have to think that much. Many smart engineers before you already have think that, and they have balanced a standard that is known as IEEE 754. I know I am talking about IEEE 754 and we are not learning it because this has so many concepts, right? That's why. If you are enjoying this, and if you have already previously studied and you learned a lot of new things, don't forget to hit the like button below. Okay, that helps, that appreciates. Okay, that tells me that whatever I am teaching, okay, that is helping you guys and you are understanding something new. Okay, nothing old. I'm not saying the same thing over again. So some question came on gate. Okay, we had this number. We had this representation and they are telling me the decimal number this has the following hexadecimal representation without normalization and rounding off. So gate just gave a surprise that they're telling me to represent this without normalization. I don't want to do any normalization here. Okay, how do I represent this without normalization? So I will not apply any normalization. Okay, I will directly represent this in this format. How to do that we'll see. They have given me xx60 the exponent follows xs64 and this is a 16-bit register. I have 0.39. So first of all, the first thing what we need to do is convert this into binary. Okay, so again that old difficult thing we have to do. So this will be 0.239 multiplied by 2. This will be 0.478 and I will store the integer value multiplied by 2. This will be 0.4.8 into 2 is 9.6, 0.9.6, what is it? 4 will go 9.56. I have to anyway get the calculator because this is not enough. Okay, so you guys also do with me. Let me just drink a bit of water. Okay, so if I multiply this by 2, again I will store this 0 here. This will be 0.56 into 2, 1.912 multiplied by 2. So again I will store this one. Divided by 2, this will be 1.824. Again I will store this one to 1.648. Again I will store this one. Now you also have to check like how big your mantissa, right? Only that much you will go. So mantissa is only 8 bits. Mantissa length is 8 bits, so I will go until 8 bits, because that's by how many precise I have to normalize this thing, right? So this is 1 2 3 4. We are only halfway through, so bear with me here. Okay, so to reduce the size of this, 1.64 minus 1 into 2 is 1.296. So 1, and this again multiplied by 2. This will be this will be 0.596, not 96, sorry, 92. How many bits I have got? This is again 0. I think I am done. So here this is 1 2 3 4 5 6 7, and last bit is left. So last bit will be 1 only, I know, because if I multiply anything greater than 0.5, I will get something 1. So I don't need to get the last result, but still for you guys I can do. So this will be multiplied by 2, which I will get 1.184, and I will stop here. Why I will stop? Because my mantissa has only 8 bits. So maximum I can only store this 8 bits. After that I cannot store anything. So it's just a waste. So like there will be a difference. I will talk about the without normalization as well. So for without normalization, actually I will solve a bit more. Okay, that will be required with normalization. With normalization, I will solve a bit more actually. So I'll solve till like 2 more bits. So this will be 0.368 0, and this multiplied by 2, this will be, anyways this was 0, so it didn't matter much. 36, and this is 0 only. Okay, so I'll store 2 extra bits. Why I will explain later on. So let's first solve it without normalization. So what is the decimal equivalent of this? Decimal equivalent of 0.239. Sorry, not decimal, sorry. What is the binary equivalent of 0.2399? Although it is not exactly equal because it will go on forever. So this will be 0 point, like after this point, right? I will just write these values in sequence. Correct? So which will be 0 0 1 1 1 1 0 1, okay, and 0 0. So this is the equivalent representation. Correct? Now what are they asking? So this is the not exact number. Exact number is multiplied by 2 raised to power 13. Correct? So exact number will be multiplied by 2 raised to power 13. They're telling me to not apply any normalization. So I will don't change anything as no normalization is required, because they have told me we don't need to apply any normalization. Okay, so I will just write this as it is. So my mantissa length is 8 bits, so I will choose this 8 bits. This will be my mantissa. My exponent will be this only. Okay, capital E will be, this is my small e, this is my small e. It will be capital E will be small e plus bias. Okay, so small e is 13. How much is bias? It is a excess 64 exponent, so I will add 64 with it. Anyways, from the bit length also you can see how many bits they have provided. They have provided total 7 bits, right? 14 minus 8 plus 1, 7 bits. 7 bit meaning what will be the base bias? What will the bias? Bias will be 2 raised to power 7 minus 1, so 2 raised to power 6. So that is 64. So this will be 77. So now I just need to write in the format. So it is a positive number. It is a positive number. So the sign bit will be 0. Sign bit will be 0. Exponent is 77. So can I write this in binary? So this will be 64. How much is 13? 13 will be 8 plus 4 plus 1. So this is 2 raised to power 6 plus 2 cube plus 2 square plus 2 raised to power 0. So what bits are actually 1? So the 0th bit is 1, then the second bit is 1, third bit is 1, fourth, 5, 6th. 6th bit is 1. My exponent is how many bits length? 7 bits. So 1, 2, 3, 4, 5, 6, 7. So exactly this one I will copy here. So this will be 1, 0, 0, 1, 1, 0, 1. Okay. Then my, what do you say? My mantissa. Mantissa is this, right? Mantissa is this only, 8 bits. Okay, remaining 8 bits. So I'll directly copy here. 0, 0, 1, 1, 1, 1, 0, 1. Okay, this is my mantissa. This is my exponent. And this is simply my sign. But they are asking me the hexadecimal. The hexadecimal representation, because obviously you can see, right, this is so bad representation. So we don't like this. We like simple things. So we'll simplify this. So from the right, I will make groups of 4. So this is simply 4. This is 8 plus 4, 12, 13. 13 is D. This is 3. And this is again D. Okay. So 4D, 3D. 4D, 3D is the option D. So it became simple and answer came. So that's fine. But let's solve the second part of this question. Just hold on. I will check if everything is recording. Yeah, everything is recording. Yeah. Let's come to the second part of this question. So if I come to the second part, right? Second part was if normalization was present. That is like that they have not asked, but what if they will ask in the future with normalization? So if I have to do normalization, nothing is mentioned, so I will use explicit normalization. So I have to normalize this thing. So if I have to normalize this thing, how will I normalize? So explicit normalization says after the point there should be a 1. So it will be 0.111101. Okay, all the others are rest are 0 only. I don't care. Into 2 raised to power, I have moved this point 2 times right. Okay, so obviously there will be, like, I have taken 2 raised to power 2 bits from here, so it will be 2 raised to power 11 now. Okay, so now this become 11. So this is my mantissa. So mantissa should be 7 bits of length, not 7, sorry, 8 bits of length. This is only 6 bits, so I have to add extra zeros, pad extra zeros here. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Sorry, this will be 8 only. Yeah, 6 I have, so pad extra 2 zeros. That's enough. That's why I padded this extra 2 zeros here. If this was like 0, 1 something, so I have to pad those as well. So this is my exponent. Okay, this is my mantissa. So what is my capital E? capital E will be 11 plus the bias, that is 64. So it will be 65 now. So this will be 64 plus 1. So it is 2 raised to power 6 plus 2 raised to power 0. So basically the 7th bit, all other bits will be 0. 1, 2, 3, 4, 5. Just hold on. 1, 2, 3, 4, 5, 6. And the 7th, the last bit will be 1. Okay. So yeah, everything is correct, right? I'm doing everything correct here. Move this 2 places. Yeah, correct. This correct. 2 places. Okay. So this will be with implicit normalization. 10. Okay. Yeah, this is second. So now I can write my bits. Sign bit will be simply 0. It is a positive number. Exponent will be 1, 0, 0, 0, 0, 0, 0, 0, 1. And my mantissa will be 1, 1, 1, 1, 0, 1. Okay. So this value will be my mantissa. This is not 6 bits, right? I have to provide 8 bits. So this is more 0, 0. Sorry. This value is my exponent and this value is my sign. Now what will be in hexadecimal representation? Again, I will make a group of 4. Okay, have I missed out something? Okay, I have messed up here. This should have been 5 zeros, right? 1, 2, 3, 4, 5. Here I have 4 zeros. So I need to pad extra 0. So this will be 4 bits. So this is what? This is 4. Here, right, I should have actually written this as well, that this is in the hexadecimal format. So this is 4, this is F, this is 1, this is again 4. So it is 4, 1, F4 with implicit, not implicit, sorry, with explicit normalization. I want to give you a homework. What is the homework? Solve the same with implicit normalization. Okay, solve the same with implicit normalization. Okay, you can do. So okay, okay, what will the hexadecimal representative of reason? Okay, I've already written the question only. Okay, so like this was supposed to be part of the second question only. Okay, anyways, so we have time. So what we can do is we can actually move this here only, this question, right? Like this is, we're anyway solving this question. So this will be third part only. So I will solve it in front of you. Don't need to waste time. So with explicit normalization, sorry, with implicit normalization, the second part is over. The third part, right? With implicit normalization, what will happen is everything will be same. Okay, so this is for implicit, sorry, this is for explicit. Everything will be same, just few things will differ here. Okay, this is my initial number, right? And for implicit normalization, what we do is there should be 1 just before the point. So this should be equals to 1.111.0.100. This should be equals to 1.111.0.100. Okay, into what I have to, like this, I had to move extra, right? So I had to move this point, shift this point here, here, then here. 3 times I have to shift. So this will be 10, like 3 will be subtracted from here because I did a right shift. So it will be 2 raised to power 10. And I will represent this in 8 bits, so this will be 0. Okay, so this is my number and this is my exponent. So my E will just be E plus bias. E is 10, bias is 64, it will be 74. Okay, it will be simply 70. Okay, did I do? Okay, I made a huge mistake. I made a blunder. Sorry for that. I made a blunder. That is what I was thinking. I am making as a mistake. This was supposed to be 75. Okay, one thing can mess up everything. Okay, this is supposed to be 75. If this is 75, then this will be, this is 11, right? So it will be 8 plus 2 plus 1. So it will be 8 plus 2 plus 1. So this will be 2 cube plus 2 raised to power 1 plus 2 raised to power 0. So here few more bits will be 1. Okay, so I was just messing up. So that's how gate also will be messed up by you guys. So this bit position will be 1. This third bit will be 1. Okay, so 1 0 0 1 0 1 1. Okay, so this will be 1 0 0 1 0 1 1. Okay, so things will change now. So just this first bits will change. So this will be, now this will be 1 0 0 1. So this is actually equals to 8 plus 2 plus 1, that is 11. 11 is B. 11 is B. What about this? This is simply 0 1 1. So this is 4 only. So it will be 4B F4. That will be your explicit normalization hexadecimal floating point representation. So this is 74 now. So just a single bit is changed, right? This bit is changed now. So this is equals to 64 plus 8 plus 2, which is 2 raised to power 6 plus 2 cube plus 2 raised to power 1, which is equals to 1 0 0. Okay, I will write from here 0 1. This will be 0, this will be 1. Yeah, that's it. 7 bits for the exponent. Okay, just a single bit has changed, right? That's it. The single bit has changed here. That's the difference. So now you can store the mantissa and the sign. Sign will be 0. This is my sign. Exponent is 1 0 0 1 0 1 0. This is my exponent, and my mantissa is 1 1 1 0 1. This is my mantissa, right? 1 1 1 0 1 0 0 0. This is my mantissa. So this is my mantissa. So now I can represent the hexadecimal format. This will be 1 0 0 1 1 1 0 1 0 1 0 0 0 1 0. So this is 4. 1 0 1 0 will be simply A. 1 1 1 0 is basically it is 1 minus, so it is E, 4AE. Okay, and 1 0 0 0 is 8. So it is in implicit normalization. The hexadecimal representation is 4A E8. This is E. Okay, so like I know things are a bit lengthy, but floating point is a bit lengthy subject. Okay, so yeah, that's it basically from this topic. Okay, so what are the disadvantages? So I told you, right, what are the disadvantages. So I will just delete this thing. The disadvantages is basically we cannot represent zeros here directly. Okay, there are underflow issues because like I have a limited range. I cannot represent very small number of range, and precision is also lost, right? I explained I have to make a trade-off, make a choice between the mantissa and precision. Okay, so this summary you can remember: more bits in the exponent means more range. More bits in the mantissa means more precision, fractional part more accurate. Okay, So that's why to solve all this, scientists made a standard. Okay, that is IEEE 754 floating point representation. This is nothing but same, but they've made few standards that accommodates the underflow, that addresses the underflow and the overflow issues. Okay, so everything is same. Whatever concept we learned, everything is same. What will be changed, I will explain that. Okay, so this Mentisa exponent, all these things you already know. One thing that will change, that as it is a standard and it is written in a scientific paper, they have written all the rules. First rule is we will use implicit normalization. We will always use implicit normalization for IEEE if we are following IEEE 754 floating point representation. Okay, so the first standard is, I will write here, because you can see from the formula, this formula is for implicit normalization. So I will write here IEEE 754 standard uses only implicit normalization. Okay, it does not use anything else, it only uses implicit normalization. Point 1. Okay, point 2, it has two formats. One is 32-bit, where my register size is 32 bits. Another one is 64 bits. It is single precision, it is double precision. Basically, we provide more bits, Mentisa has more bits, exponent has more bits. So range also increases, precision also increases. Mainly we give the higher bits to the Mentisa. As you know, the higher the Mentisa bits, the higher precise my system is. So just two standards. One is single precision, another one is double precision. Okay, more bits, more precise. That's why double precision. Okay, and like how is it exactly more precise? I will explain that. Because everything here, right? Everything is fixed. So you have to remember few things. If you remember, if you have ever done programming, that you used to store, you had two variable types. One was float, another one was double. Okay, and if you have done a bit of competitive programming or something, right, then in there, right, you have to keep everything precise. Basically, you should use the minimum storage, minimum memory, and you should solve the question faster. Okay, your code should take the minimum storage and it should solve the question faster. Now, in a particular question, if you didn't need that much precision, you should not choose a double type variable, because a double type variable has, in C, it has 8 bytes. 8 bytes meaning 64 bits. 64 bits exactly matches with this double precision. So basically, internally, it is following the double precision rule. Okay, it is following the double precision. So we don't need that much storage. Okay, if your like number is not that low, you can use float. Float only takes up 4 bytes. Each float variable only takes up 4 bytes. What is 4 bytes? 32 bits. That is basically single precision. So internally, they are actually using this IEEE 754 standard. Okay, so that is the main thing that I wanted to explain here, that according to the storage constraint, you will use whatever variable you have to choose. Always options, having options is always better. Okay, but not having, like, it's not like a person should have 2 girlfriends or a girl should have 2 boyfriends. That option is bad. Sometimes having more options is bad, sometimes having options is good. Okay, it depends on the perspective, but here having more options is good thing. Okay, so we will choose according to our requirements. Now, few things are fixed here. So this you have to remember. This needs to be remembered. What needs to be remembered? These values, right? Okay, just remembering one is enough. So in single precision, I have total 32 bits. out of those 32 bits, 1 bit is assigned for sign bit, that is fixed. 8 bits I will use for exponent. It is fixed. It is fixed. All of this is fixed, okay? It is not variable. It is on a standard paper. It is a scientific paper. So it is standard. We use this standard. We don't change this, okay? So it is fixed. So 8 bits will be given to exponent and the remaining 23 bits will be given to the mantissa. So only you remember the exponent, that is enough. And in double precision, our exponent increases, but not by that much. Only we increase our exponent by 3 bits. But our mantissa is more than double. It is 52 bits. So it is more precise. More bits to mantissa, more precise. Okay. One more thing is that this thing you have to remember. These 2 bits you have to remember for double precision and single precision. One more thing what you have to remember is the bias. So up until now, what we have been remembering till now is that my bias will be 2 raised to power k minus 1, correct? Which is here for single precision, my bias is 2 raised to power, like it can have 2 values, 2 raised to power 8 minus 1, that is 2 raised to power 7, which is 128. Okay, and here my bias will be 2 raised to power 11 minus 1, that is 1024. Okay, now scientists are very smart, so they actually didn't choose this bias 128 and 1024. They actually chose a number lower than this, 127 and 1023. Okay, they actually chose a number lower than this. This was supposed to be the bias for conventional system, but for IEEE 754, the standard, these 2 will be biased for single precision and for double precision. So this, right, this also you have to remember the bias values. It's very simple to remember. Just remember the excess code, that should be enough, and just subtract an extra 1. Why we are subtracting an extra 1? What is the reason? Actually, what we do is, we, like, one value has been reduced, right? One value has been reduced. So my minimum number was minus 128. Now if I do minus 128 plus 127, I get only minus 1, and which is not unsigned, right? So what we do basically, this state, right, this state, this minus 1, I cannot represent minus 1. This state is reserved for special values that I will come to. This state is reserved for special values. Okay, so now those zeros and all those things, right, will be reserved for this state. So this you don't have to understand. If you couldn't understand, that's fine. Just I'm telling you, giving you the reason why have we chosen 127 as bias and not 128. I just used that extra 1 state to store something else. Special numbers will store. Okay, reason. Ignore this. You can ignore this. Just understand that the bias will be 127 and 1023. Okay. Now, first thing is my normal numbers. Whatever up until now the floating point representation, what we are learning, those will not change, right? Those will be simply same. So in my floating point representation, if my E is not all zeros, this is E is not equals to all 0. Okay, it should be all zeros. Okay, all 0 and all 1s. If my E is not equals to all zeros and all 1s, then this is a normal number. So my E can be, so my sign bit can be anything, my E can be anything, my mantissa can be anything. Okay, I don't have any boundation on these values, except my E should not be equals to all zeros or all ones. Then how can I represent my number? My number will simply be this mantissa, 1 point this mantissa, whatever the mantissa I have, okay, here, raised to into the base. Obviously sign is here previously, sign was always there, we don't do anything with sign, into 2 raised to power the exponent, like this is what E, right? And what is E? If you remember, E plus bias was my capital E, so my small e will be capital E minus bias, so this will be capital E minus bias. Whatever we have been learning, that much only, but only difference is this: we are using implicit normalization. Implicit normalization. Okay, now we'll come to this denormalized number just in a second. Okay, so this should actually have been 2. They messed up. I will come to this denormalized number just in a second. Okay, first we'll understand the other special cases. So few special cases I have. One special case is if all E is 0 and M is 0. Previously in implicit it was allowed all E and M were 0, but it was not representing 0. But now IEEE standard has told me, okay, they have a standard that they told me that if my E is all 0 and mantissa is all 0, that is, it is all 0. I use some other color. All 0 and mantissa is also all 0. And if sign is 0, this represents plus 0. This represents plus 0. And if my sign is 1, but mantissa and exponent are all zeros, this represents minus 0, which is not a problem. Arithmetically, it will not make any difference. If I add a plus 0, a minus 0 is still a. So computer can do that. Computer is that smart. It is not that dumb. Okay. So it's okay. We have 2 representations for 0. That is fine. That is not a problem. Okay. But remember this will only happen, like our special cases will only happen if, just these things you have to remember, if your E is all ones and all zeros. Okay, if your E is all ones and all zeros, then you can simply like this will be the special cases. And one of those special cases, if E is all 0 and mantissa is also all 0, then you will get either plus 0 or minus 0 depending on the sign bit. Point 1. Point 2 is infinity. Previously we were not able to represent infinity. Infinity represents means we are in a overflow state. There was no way to represent a overflow state. Now what we are doing, if my E is all ones and mantissa is all 0, that represents that I have got overflow. That represents that I have got overflow. So if my E is all ones and my mantissa is all zeros, okay, that represents a overflow. Now overflow in the positive side or the negative side, that will be explained by the sign bit. Okay, so if my sign bit is 0, that represents plus infinity, and if my sign bit is 1, that represents minus infinity. Exponent is all 1 and mantissa is all zeros. This is the second special case. Third special case is if my exponent is all ones and mantissa is not equal to 0. It is don't care. Like here, right? Whenever I write x, right? X means what? X, if you have studied digital logic, it means don't care. Don't care means I don't care if it is 0 or 1. I don't care whatever it is. Okay, I don't care. Can be 0 or 1, anything. But I don't give a shit. I don't care. Okay, so this will be here the third special case will be not a number. Not a number meaning if I have all ones on the exponent, and sign bit can be either 0 or 1, it doesn't matter. Okay, sign bit can be 0 or 1, it doesn't matter. And manticize anything that is not 0. Manticize anything that is not 0, then it will represent not a number. What does not a number means? Not a number means it is used to represent the number that my system representation cannot represent. Although it is it can be a real number, but we cannot represent it. So just like limits, right? 0 over 0, infinity minus infinity, those limits, right? Those are not a number. Okay. So these are the three special values. Okay, these are the three special values. Now I will come to the denormalized case. When does my CPU will understand it is a denormalized number? That is the point one. How will my CPU understand it is a denormalized number? Denormalized number means it is just a fraction. Just a fraction. It is a fractional number. Okay, I will come to this, don't worry. I will, in the next few slides, I will explain. But when does this happen actually? So we have discussed for the case when all E is 0, all M is 0. Okay, we have discussed for the case when E is all 1, M is all 0. We have discussed for the case when E is all 1, M is don't care. We have discussed for the case where E is don't care, M is don't care, but it should not be all zeros or all ones. One thing is missing. We haven't discussed for the case where E is all zeros and M is don't care. We have discussed for the case where E is all 1 and M is don't care, but we haven't discussed for the case where E is all 0 and M is don't care. Now we'll discuss about this. This denormalized number happens when my E is all zeros, M is don't care. M can be anything. Then my CPU, then my computer understand that it is a denormalized number. What is denormalized number? I will come to it. Don't worry, I will come to it. Sign bit can also be anything. It can be negative or positive. Okay. So here, what we do is, denormalized numbers are a special case in, like here, this is the first point. In IEEE standard, we only uses implicit normalization that we already know. Okay. So next point is the denormalized number. What is denormalized number? Denormalized numbers are special cases in IEEE 750 standard used to represent values very close to 0. So this actually solves the problem. Solves the problem of underflow. They extend the range of the representable values by allowing leading digit of the mantissa to be 0 instead of it requiring to be 1. Okay, so without the denormalized numbers, values smaller than the smallest normalized number would result in underflow. Denormalized numbers provide a way to represent the values instead of truncating it. Okay, so we'll understand this with this question, right? What is the minimum possible value of E? What is the minimum possible value of E? Okay, the minimum possible value of E in the normalized, when we are talking about normalized numbers, is 0, 0, 0, 0, 0, 1 in binary. Why? The all zeros and all ones are already reserved for special cases. This I am talking for normal case. In normal case, minimum possible value of E is 0, 0, 0, 1, right? This is for the normal case, excluding special cases. This is the minimum possible value that E can take, that is 1. comma 2, or it can be written same as in decimal. What can be the exponent then? Exponent is 1 minus the bias, that is 127 in IEEE 754 standard. It is minus 126. Okay. So what number can I represent? It is minus 126 for 32-bit, and for 64-bit it is 1 minus 1023, that is equals to minus 1022 for 64-bit. Okay. So if my mantissa, like this is just a normal number, right? And mantissa can be anything. Mantissa can be anything, right? Mantissa is a don't care. Mantissa can be anything. So mantissa can be here all zeros, right? That because I want to choose minimum possible number, mantissa I can choose as all zeros. So if I choose all zeros, if my mantissa is all zeros, right? If my mantissa is all zeros, mantissa is all zeros. Okay. So if I convert it back into my implicit conversion, how will I convert it? So implicit normalization, if I do, okay, 1 will be there because we are using implicit normalization, right? 1 point, how many zeros total? Like I don't care, everything is 0, I don't care. This into either 2 raised to power minus 126 or 2 raised to power minus 1022. What did I use? I used implicit normalization. Okay. So I used implicit normalization. So after I used implicit normalization, so if I am in the 32-bit IEEE standard, so this number can either be equals to 2 raised to power minus 126 or 2 raised to power minus 1022. So this is the minimum possible value that can be represented in normalized format. Okay. This is the minimum possible value that can be stored in normalized format. This is the this minimum possible value that can be stored in normalized format. Okay, now if it is not normalized, it is denormalized. That means how does the computer understand it is denormalized? When my exponent is all zeros but my mantissa is not 0. If my mantissa is not 0, that means my computer understands that it is denormalized. So now this is the minimum denormalized representation. Okay, not denormalized. So this is the minimum normalized representation. Now I will represent in denormalized fashion. So in case of denormalized, what happens in case of denormalized? My exponent is all zeros. My exponent is all zeros. Okay, my exponent is all zeros. So if my exponent is all zeros and they have a very specific thing that they explain here, your number can be represented like this. It doesn't need to be 1 here. It can be represented 0 point the mantissa, right? It uses, like it doesn't use, this is not any implicit or explicit. This is not any implicit or explicit normalization. We are not using any normalization. We are denormalizing. We are not using any normalization. We are writing the mantissa as it is. So the formula is 0.m into 2 raised to power 1 minus bias. That is the formula. This is fixed. This thing is fixed. So how does it help? I'll explain how does it help. So let me take this value. So mantissa can be anything, sign can be anything, right? So I will choose my mantissa to be, it will not be all zeros, because if it is all zeros, that means it is representing zeros. I cannot choose all zeros. So minimum value of mantis I will choose. Minimum value of mantis M. This will be like, I cannot choose 0 because 0 is not allowed. 0 has already been taken by the plus 0 sign. Okay, it will be 0 0. It will go on till the last bit is 1. Last bit is 0 1. Okay, it will go on. How many bits are here? How many zeros are here? If it's for IEEE 754 standard, right? In 32 bits, 23 bits are mantis bits. So overall I can give 22 zeros. This will be 22 zeros. Okay. Now this is 22 zeros. Now how can I do the back calculation? So what is the formula? Formula is -1 raised to power s into 0.m into 2 raised to power 1 minus bias. That is the formula. Okay, this is fixed. This thing is fixed. So I will assume my sign bit to be 0. So it will be this thing only. So 0.000 and it will go on till 01. How many zeros I have? 22 into 2 raised to power 1 minus bias. What is 1 minus bias? 1 minus bias. Bias in this case is for 32 bit, it is 127. Okay, you can do it for the 64 bit. So how many? I have 22 zeros. It doesn't look good, right? It doesn't look good like this. So I want to right shift this point after this one, because humans like whole numbers, they don't like fractional numbers. So how many digits I have to right shift? This is 22 zeros plus the extra one, 23 digits I have to right shift. If I want to right shift, I have to subtract from the exponent. So it will be 1.0 into 2 raised to power minus 23, because I right shifted by 23 times, into 2 raised to power minus 126. Okay, so now can you see a difference here? Now I can represent 2 raised to power minus 149. Previously with 32 bit IEEE standard, my minimum value was 2 raised to power minus 126. Now I can represent 2 raised to power 149. You can choose other values as well. You can choose mantis to be anything, whatever you wish for. You will see you are able to choose so many lower values now. Previously you are not able to do it. Okay, so that is the main thing about denormalization. I want to go in depth, but I don't want to go too much in depth because that will just take up most time, and I don't want to go too much into this floating point representation. This much knowledge is enough. If you want to dig deeper, you can choose another examples for M. Okay, and that should be enough. So this solves the problem of underflow. Now I can represent even smaller numbers. Even smaller numbers are represented, which I know are only fractional numbers. So here computer understand this is only a fractional number. This is only a fractional number. Okay, that's why we get so much range. So this is just the summary of denormalized number. Exponent has to be 0 and your E will be fixed, that is 1 minus bias. E is fixed, that is 1 minus bias. Actual exponent will always be 1 minus bias. Okay, this is fixed. This thing is fixed. You don't need to do any implicit blending, that is you don't need to do any implicit normalization. We are not doing any normalization. What we are doing, we are directly copying the mantissa. Let me take another example. Okay, let me take a simple example. So if this is 130 zeros, 120, 120 is there. So if I have a number mantissa like this, right? If I have a mantissa like mantissa is this 0 0 0 1 0 0 and it is 0 until then. Okay, and my E is all zeros. E is all zeros and S is 0. Okay. If I do normalization, how will I do the normalization? So if it is normalized, so a 1 will come here. Okay. Because it is implicit normalization, it will be 1.001 into 2 raised to power. Assumption will be that I am doing like okay, let me just take one example. This is one case where E is all zeros, and the second case is same. Mantissa will be same. Okay, sign will be same, just the exponent will change. So these two things will be same. In one case, exponent will be all zeros, and in the other case, exponent will be like the minimum normalized value, that can be 0, 0, 0, then 1, 0, 1, right? This is the minimum possible value. So here, I will not do any implicit normalization. So I will directly copy my mantissa as it is, that is 0. I know it is a fractional part, so it will be 0.001 0001 into 2 raised to power 1 minus bias. I am assuming 32 bit, so 1 minus 275, that is 0.001 into 2 raised to power minus 126. So this is the value, and I want to see everything in like simple terms. So I will right shift this point 4 bits. So this will be 2 raised to power minus 130. So I can represent this mantissa, can represent 2 raised to power minus 130. Okay. What about the other case? If it is normalized, then this can only represent what? This mantissa will come with a 1.0001 into, because it is, I am applying implicit normalization, into 2 raised to power exponent minus bias. So exponent is 1 anyways, and bias is 127. So it is 1.001 into 2 raised to power minus 126. So can you see the difference? So this is my 2 raised to power minus 126, and this is 2 raised to power minus 130, right? And like this is almost equals to 1, negligible. So we can even go below my lower values if I don't do any normalization. Why is normalization important? Because we need to have a standard, right, to represent. Why is normalization important? Because of this problem. 1.01 can be written as 0.101, or can be written as 0.00101, or can be written as 10.01. Just this multiples will change, right? To solve this thing, we had to introduce normalization. But normalization has also its own problems. So to solve that, we introduced denormalized values, which increase the underflow range. Okay. So here those things are only written. Smallest positive denormalized value can be equals to this, right? So the smallest positive value that I have computed here, the smallest positive denormalized value in 32-bit representation will be 2 raised to power minus 149, and like for 64 you can solve that, right? So that was about the this denormalized numbers. So normalized numbers, here we use implicit normalization. Here we don't use any implicit normalization. Here what we do, we just simply copy paste the mantissa 0.m. That is it. Simply whatever mantissa I have, I directly copy it. Okay, it extends the range closer to 0, and it gives larger range overflow. Okay, overflow larger range. Smallest representable number is this. Okay, and here the smallest representable number, like the whole mantissa bits will come into factor now. So whatever bits I had for mantissa, that also can be used for representing the smaller numbers. Okay, so this will depend. Everything is written for 32-bit here. So this will be total 23 digits, right? 23 digits. That is 22 zeros plus 1 number, right? So this can be written as 1 into 2 raised to power minus 23 into, okay, this eraser is big, into 2 raised to power minus 126, which will be equals to 2 raised to power minus 149. So obviously the underflow increases, so all those things are there, so I will not go too much in depth here. So now we will solve few questions. So what I want you to do is pause the video and try to solve the question and put in the comments below what were your answers, so that this will be interactive, right? So that you are able to like understand and implement this concept. This is the first one, second one is here, third one is here, and fourth one is here. Okay, so I think this is the last. Okay, one more question I have. Yeah, this is the last one. 14 is the last question. After that we don't have any question. Okay, so pause the video and try to solve all these questions by yourself, then I will solve. Let's start off with this question. So we have to represent this decimal value in the IEEE 754 standard, which has 32-bit floating point. So they have given you this what does each bit represent. Okay, but still they may decide to not give it. Okay, it's their choice. So I observe that I have to represent minus 14.25. so in binary, what this will be minus 1 minus into 14 can be represented as 8 plus 4 plus 2. Okay, 8 plus 4 plus 2. So 8 plus 4 plus 2 is simply 2 cube plus 2 square plus 2 raised to power 1. So this will be 1110.01. So this is what 0.25 is, correct? 2. Okay, but I have to do implicit normalization. So this will be minus, so sign bit is anyways 1, so from here I can ignore the sign bit, as sign bit will be 1. This can be written as 1.11001 into 2 raised to power 1.11001 into 2 raised to power 3, correct? Because I moved this point left 3 times. So this is 2 raised to power 3. Now this is my E. What is my bias? It is a 32 bit representation. In 32 bit representation, my bias is 127. So my E will be small e plus bias. So it is 3 plus 127, that is 130. How can I represent 130? 130 can be represented as 128 plus 2, that is 2 raised to power 7 plus 2 raised to power 1. So it will be equals to, so 7th bit will be 1. So this is 0 1, then this is 2nd, 3rd, 4th, 5th, 6th and 7th. Okay, so this is my exponent. So exponent should have 8 bits. Okay, exponent has 8 bits, which is correct, right? Here it is 1 2 3 4, 1 2 3 4. What is my mantissa? Mantissa is this, right? This is my mantissa. So now I will write everything. So sign bit is 1. This is my sign bit, that is 1, as it is negative. Then I will write my exponent. Exponent is 1 0 0 0. Okay, I have how many zeros? 0 0 0 0 0. So 5 zeros I have. 0 0 0 0 0 5 zeros. Then 1 0. Then I have mantissa. Mantissa is of how many bits? Mantissa, they have given me space for 23 bits, but obviously I can add zeros here, that I don't care. 1 2 3 4 5. Only 5 bits are of use to me. Okay, 1 2 3 4 5. Then all the rest are zeros. So I have to be bit careful here actually, because I have to represent in hex, right? I can observe only the first few bits are important, right? I can ignore the last, because everywhere the last bits are always 0. Last bits are always 0. So I don't need to do the conversion for the last bit, and I know that it is totally a 32-bit number. This will be a 32-bit number. So I can be a bit like relaxed, that I don't need to care about grouping of 4. Everything will be grouped by 4 if I come from the left and come from the right. So I'll come from the left and group by 4. Why? Because it is a 32-bit number. 32-bit number will have how many groups of 4? It will have 8 groups of 4. That is for sure. I will not have, if I had 31-bit number, then I would have had to come from the right hand side to the left, because I had 31 bits. I had to add extra 0 here to make it 32, so that I can make group of 4s. Getting the point, right? 32 bits, so everything will be 4 bits only, so I can come from the left as well. So from the left I will choose 4 numbers, 1100. So first number is what? This is 12. 12 is C. So first number should be C. So these two options automatically get eliminated. Okay, because first number should be C. What is the second? Now if I observe, second number is common, right? Second number is common here as well, common here as well. The fourth number is changed. So obviously after 4 we will see the change. So second number is what? This is 0001. So this will be 0001. So it is 1 only. 0001, it is 1. Then it is 0110. 0110 is 2 and 4, that is 6. Okay, it is 6. Then I come to 0100. 0100, which is, this is 4. So it will be 4. So it will be C164. C164. Okay, just hold on. Let me check if I am not making any mistake over here. Mantisa is 1101, correct? It is 0. Yeah, it is 0.1 is correct. Is, yeah. So it should be C164. Yeah, C164, option A should be your correct answer, right? Because like this is just the notation. This much only we have to solve. We don't have to solve all the bits. All the rest are simply 0. So we can ignore those. We can simply ignore those. Okay. So now let's come to the 11th question. So if I come to the 11th question, what are they telling? They're telling me the format of the single precision floating point representation of a real number is, according to the IEEE standard, is given. Which of the following choices is correct with respect to the smallest normalized positive number? So they are asking me the smallest normalized positive number. So if it is a normalized number, then the special cases are gone. It can't be a special case, right? What were the special case? If E is equals to 0, all zeros or all ones. So here I see E equal to all 0, not possible. Here I see E equal to 0, not possible. Here I see E equals to 1. Yeah, E, smallest possible value of E can be 1. These are correct. But here they are telling me mantissa is all 0, and here they are telling me mantissa is all 1s. Can mantissa be all 0? Yes, mantissa was don't care, if you remember. It can be all 0. This is the minimum number. Here if I convert it back, right, what it will give me, this will be 1.0 all zeros into 2 raised to power exponent is 1 minus the bias, that is 127. Okay, so this will be 1.00 into 2 raised to power minus 126, and this will give me what? This will give me 1.00, whatever many zeros I have. How many zeros I have? Total 22 zeros, then 1. Okay, into 2 raised to power minus 126, same exponent will be same. Both are almost equal, but this number is slightly larger than this number. So obviously the smallest possible number they have asked. So option C will be correct. Option D will be incorrect. Okay, so let's solve the next question. So this next question is also very interesting because it's bit lengthy. You have to compute the equivalent of all this, right? You have to compute the decimal equivalent. What are they telling? They're telling me that we have 3 floating point numbers and they are stored according to IEEE 754 single precision. So single precision floating point number, so it will be 32 bits, and each register has 32 bits of content is in them. Okay, these are represented in hex, right? 0x meaning these are represented in hexadecimal. They are telling me which of the following is true. Like if I perform some arithmetic operations with the numbers, which of the following will be true? Okay, so this, right, you just simply have to, which of the following is false, not true, sorry, actually which of the following is false, just be careful. So you just simply have to find out all the numbers. So first one I will find out. First one is RA. So A is 0x C14 0x C14 000. Everything is 0 after this, so it wouldn't matter. Only first few bits are important because for all the cases, right, it is 0. The last few bits are 0. So if I convert it back into binary, so what is C in binary? C in binary is 1100, right? It is 12. What is 1 in binary? It is 0001. 4 in binary, it is 0100, and everything else is 0 simply. Everything else is 0. Okay, the rest is 0. So from here I can see the sign bit. This first bit is the sign bit, right? So my S is actually equals to 1, so it is a negative value, and after it, right, 8 bits are actually my exponent. So 1 2 3 4 5 6 7 8. So this exponent capital E is equals to 2 raised to power 7 plus 2 raised to power 1. So this will be 120 120 what am I talking about? So yeah, 128 plus 2, that is 130. It is equals to E plus bias. So my E will be equals to 130 minus 127. So E is equals to 3. Now I can convert it back. This is my mantissa. Mantissa is starting from here. Okay, so mantissa is 100. So basically it is 1.100, whatever, I don't care. So my number will be minus 1.100 into 2 raised to power 3. So it is basically equals to minus 110. Okay, 1 2 3. This is my number. So what is this? This is basically 12, minus 12. This is in binary. In decimal, this is minus 12. Let's solve the B. Okay, it took me so much time to solve the AB. I will solve the B as well. So B will be 0x421. So what I will do is I will solve, I will do the conversion and then I will come back with the solution of the question. Okay, so I have solved the values. So B, if you do the back conversion, right, if you do the simple back conversion, remember your bias is bias for IEEE 32-bit convention, single point precision, it is 127. So if you do the back calculation, this will come out to, B will come out to be 36, and your C will come out to be plus 12. C will come out to be plus 12. Now let me eliminate each options. So like I will write here only A is equals to minus 12, B is equals to plus 36, and C is equals to plus 12. Okay, ABC equals to plus 12. So A plus C is 0, which is correct, but they are telling me which is incorrect. So this option is eliminated. I need to find out which of the options is wrong. C is equals to A plus B. C is equals to A plus B. which is not correct. C is not equals to A plus B. A plus B is 24. Okay, so obviously option B will be incorrect here. But let's obviously for our college ki thandak, we will do the option C and D as well. So B is equals to 3 into C. B is equals to 3 times the C, which is correct. If I multiply 3 here, I get 36. So obviously this is correct. So this will not be my correct answer. B minus C is greater than C, but greater than 0. B minus C is greater than 0, which is correct. 36 minus 12 is 24, which is greater than 0. So again, this is also not my correct answer. Obviously, option B is the correct answer. Okay, just it can be a bit lengthy, but this kind of questions will come in your examination. Okay, next let's solve this 13th question. So here we have to consider like this IEEE floating point representation. P and Q are given. We have to tell the floating point single precision format of the multiplication of P and Q. Okay, of the multiplication of P and Q. How will you go about this question? So first thing is very simple. You convert this back into decimal. You convert this back into decimal and then do the multiplication. That is what I will also do. But few things you can do to eliminate, that I will come to. That option elimination I will come to. Okay. So first let me convert this. Let me convert this into decimal format. So this P is equals to I will just convert the first few bits. Okay, until 0xC18. I will not convert the bits after it. Why? I will explain. Okay, 0xC18, 0xC18, other bits are 0 only. Okay, 0xC18, other bits are 0. So this will be 1100. Okay, 1100, and this is 0001. This is 0100, not 010, sorry, 1000, and rest are 0, right? All zeros. I don't care about those. So I can see sign bit is 1. Okay, sign bit is 1, so it will be a negative number. Then I will, my other next 8 bits will be the exponent. So 1 2 3 4, 1 2 3 and 4. This much will be my exponent. Okay, and I can see my Menti size all zeros. So it is basically 1.000 into 2 raised to power. What is it? It is 2 raised to power. This is my exponent, right? So this is equals to what? 2 raised to power 7 plus 2 raised to power 1 plus 2 raised to power 0. Okay, so my exponent comes out to be what? Exponent comes out to be 128 plus 2 plus 1. So it is 131. So my E will come out to be what? E will be 131 minus 127, that is 4. This is what my E will come out to be, right? So this will be 2 raised to power 4, 1 into 2 raised to power 4, and sign is negative, so it will be minus. Okay. What about Q? Okay, I will not solve the whole Q because the day will be over if I solve the whole Q. Okay, so 0x 3f5c. Okay, 3f5c. Am I correct here? 3f5c. Yes, 3f5c. Okay, so this, if I now break it down, this will be 0 0 1 1. This will be all ones. This will be 0 1 0 1. This will be 1 1 0 0. Okay, here my sign bit is 0, so it will be a positive number. That is my first observation. So I'm multiplying P and Q. One is negative, another one is positive. So result also will be a negative number. Result will be a negative, something negative. I got this information. So from this I can say the result of the P and Q the sign bit will be 1. Okay, sign bit will be 1. What is the exponent? Exponent is this, right? 1 2 3, just hold on, 1 2 3 4, 1 2 3 4, this much is the exponent, and from here mantissa is there. So mantissa is this, so it will be 1 point, it starts from here, right? It starts from here, 1.10111, and it goes on. Okay, I will write this later on. 1.101. There are some things that I ignored. Okay, now this is what? This is basically E, and my E is 2 raised to power 1 plus 2 square plus 2 cube plus 2 raised to power 4 plus 2 raised to power 5. Okay, how many ones I have? This is the 1 2 3 4 and 1 2 3 4. Okay, so I start from here, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, 2 raised to power 5, 2 raised to power 6. What is this basically? This is equals to, like, this will be a bit difficult. So 64 plus 32 plus 16 plus 8 plus 4 plus 2. Okay, that's it. So it is, this is 10, this is 20, 30 plus this is 96, 30 plus 96, 30 plus 96 is 126. Okay, am I correct? 30 plus 96, yeah, 126. So my exponent capital E is this, but what is my bias actually? My bias is not my bias, sorry, my E will be capital E minus bias, that is 127. So it will be minus 1. Okay, my this small e, right? Small e comes out to be minus 1. So it actually helps me. Why? Because this number, if I multiply this with 2 raised to power minus 1, this is 0.11011. Okay, I can neglect this values. Okay, what we can do is we can approximate, or you should not approximate actually. What we're doing is we're multiplying 0.001, right? This first number will be negative, and this number is what? This is 1 point something into this 0.022. So this two if I multiply, right? These two if I multiply, 1.00 into 1.1011, and I have 2 raised to power 4 here, 2 raised to power minus 1. So what will happen? This will be 1.00 into something 1.10111 into 2 raised to power 4 minus 1. The exponents are getting multiplied. So exponent, what will happen is this one will stay, correct? This one will stay at the top. After point there will be some values. I will for now ignore those values. There will be some values. I am not doing the calculation. I want to save time. Multiply it by 2 raised to power 3. Okay, this format is what? This is my normalized format. In normalized format, I observe that my exponent is 3. Small e is 3. So what will be capital E? Capital E will be small e plus bias, that is 127. So it will be 130. So if exponent is 130, it is equals to what? It is 2 raised to power 7 plus 2 raised to power 1. So it is basically 0, 1, then second, third, fourth, fifth, sixth, and seventh. Okay, so my sign bit is 1. This information I already know because I know my result will be negative. Then I will add the exponent. Exponent will be 1 0 0 0. There will be so many zeros. 1 2 3 4 5. 1 2 3 4 5 and 6. This is my exponent. Okay, then I have the mantissa that I am not calculating. Okay, Without this, can I still be able to get to my option? Yes, I will be able to. So I have to group 4 bits. So these are the group of 4 bits. Then these are the next group of 4 bits. These are the next group. Okay. So from here, what is the value? That is C. This is C. Then I have, this is 1. Okay. This much I know. The first hexadecimal of the first 2 digits will be C1. So C1 is here and C1 is here as well. Okay. So these 2 options are my possible answers. These 2 options are my possible answers. Now how will I solve it? Now, okay, I missed a point here actually, like this, right? I'm multiplying 1 with anything. If I multiply 1 with anything, I get that same value only. So this will be the same value, right? It will be 1.0111. I will get the same value. So this, right? Now we can simply solve this matrix. Actually, I missed this point. This will be 1000111. Okay. So if I now group these 5 bits, this 4 bits, it will be 0101. So it is 5. So from here only, I don't need to solve further. From here only, I can say that after C1, 5 should be there. So obviously option C will be correct. So like I was wrong here. Like they will not do any injustice to you. They will give some question that is solvable. So that's why like they gave this one so that this simply gets the multiplication. I missed. I had an oversight during the first time. Okay. So let's solve this next question. So next question is this format is given for IEEE standard. Choose the largest floating point number among the following options. What can be the largest floating point number? Okay. So for the largest, right, exponent has to be the largest. Exponent has to be largest, but exponent equals to all ones not allowed. It is a special reserved number, right? So obviously all ones will not be allowed. So I will not be able to choose this number. Okay. This is wrong. All ones is a special case, correct? So obviously I will choose slightly smaller than this. What is the lower value? Okay, just below this. If I subtract all from all ones minus 1, right? So this last bit, if this last bit is not set, that will be the value just below this, right? So obviously this has the option B, I can see has the highest exponent. And if the exponent is highest, so will be the E. If the E is highest, so will be my maximum number, because mantis size for all these cases anyways 1. Anyways, this is not possible. Mantis size 0 is not possible. For these cases, mantis size 1, okay, fine. But exponent, this has larger. So I will multiply this more times. So obviously option B will be correct. Okay. So that's how, like in GATE 2024 also, recently they are giving questions. So every year you can expect 1 question. So like what are the standard, what are the advantages of IEEE 754? Just for theoretical point of view, it ensures compatibility across platform. This is actually used in our computers and everywhere. Wide range, it can represent very small numbers and large numbers. It handles scientific calculations with very good accuracy and precision. Okay, that is the advantage of this IEEE 754 representation. And with this, we are done with our number representation, floating point number representation. I hope you have enjoyed this topic. I know this topic may sound very boring at first, but I have tried to make it as interesting and as conceptual as possible. Trust me, whatever you have studied, right, you have studied the best, you have studied from the best resource. You have the complete knowledge of floating point representation, everything from normalization to denormalization, from biasing, why are we using the biasing, why we needed floating point representation from fixed point representation, then why IEEE 754 came. I have totally given you a story. Okay, so I hope you have enjoyed this video. If you did, please do hit the like button. Please comment down below how you're enjoying the lecture. Okay, and make sure to visit our website PrepFusion.in for more courses and more things. I hope you enjoy. Until then, I will see you in the next lecture. Thank you for watching.